So good afternoon. So welcome to UC San Diego for the Harry Wieder Symposium on his 100th birthday. Many of his friends and former students are here from across the United States and around the world. Arizona, Michigan, Singapore, Canada, Hong Kong, and Israel. So maybe can the out-of-town guests stand up and be recognized? Yeah. Yeah, thank you very much for coming all the way here. So 30 years ago, I organized a surprise 70th birthday symposium for Harry. And 2 years ago, I was talking with Nikki Shigeru and Juan Fernandez about a 99th birthday gathering, last year. But I regret that we cannot organize such a gathering when he's alive. But I'm very happy that all of you are here to honor Harry's lifetime achievement. So I would like to now introduce to you Bill Lin, our department chair, to say a few words. Yeah.
Thank you, Charles. Good afternoon, everyone. Thank you for being here today to honor our friend and colleague, the late Professor Harry Wieder. I just want to add to Charles' welcome to you that we really appreciate your support and friendship, and I'm honored to welcome you today as we celebrate Harry's life and achievements. Harry's family is here today. I hope that you'll enjoy hearing about your father's or your grandfather's work from his former colleagues and students to see all the wonderful things he has contributed to our field. And as Charles mentioned, many of presenters today have traveled from very far away, including many people from around the world. So thank you very much for coming. One of the things that you'll hear about today is that Harry has always had a very deep passion for helping our future generations. And with that, I'm very happy to say that through the generosity of Harry's family, we've been able to establish the Harry Wieder Award in Electronic Materials Excellence, which will be his legacy at UC San Diego. And this award will ensure that our future generations will continue his footsteps in the fields of electronic devices and materials, material science, and nanoscale devices and systems. So thank you for Harry's family's generosity. So before passing the podium back to Charles, I would like to take a moment to thank the committee for arranging this program for you. Charles, Charlie, and Rachel have spent a lot of time working hard to organize this event today. So please give them a round of applause. And so with that, I'm going to pass the podium back to Charles. So thank you. Welcome.
Thank you. Okay, so this is the symposium I organized in 1989 on June 10th. So just for Harry's 70th birthday. And here I can control this. So it's on semiconductor interfaces and heterojunctions. So that's the two topics in Harry's research. And so you see here, I invited many of Harry's friends, like Bill Spicer from Stanford, Tom McGill from Caltech, and Professor Lu Xiang from UC San Diego, and Carl Williamson from Colorado State. And so here you see to honor Harry Wider's 70th birthday. And it was a surprise to him because I did not mention to him, and he was so surprised when he saw Herb Kromer from UC Santa Barbara on campus. And so now I want to, here is a list of speakers. And now I want to introduce to you our next speaker, Professor Lu Xiang. because you see Lou here, he spoke at that symposium. Yeah. Carl Wilson was going to come today, but he canceled because his wife fell ill. So Professor Lu Xian is a professor emeritus at the physics department at UC San Diego. So let's welcome Professor Lu Xian. Yeah.
Thank you, Charles. I'm glad to see so many familiar faces here.
Could you get close to the microphone, please?
Oh, all right. There's a voice. Hi, David. Yeah, I move away because of the lights, but I guess I have to go with that. I think I got to know Harry from serving on the engineering PhD exams, and I see some formal candidates, well, they got their PhDs here, like Rachel, Cindy, Juan. I haven't seen Juan yet. And Norman is here too. I don't know, Norman, were I on your committee? Oh. I couldn't remember. So I hope you don't bear grudges. Yeah. In the process, I found out Harry was a great mentor for his students, but he was also a great explainer for me because I did not understand where these engineering things are going. And he was very patient in explaining it to me. So at that time, about the 80s and 90s, I was mostly interested in excitons and the spin effects from optical controls. So I got to talk to Harry, and he used to worry about the materials, the interface. He said, he says, some of these things, are you sure you can get it done, things like interface defects and impurities and so on. Well, it was good to learn that because otherwise I'm not sure that we can actually do what we promised the funders. Actually, he pointed that out about the funders. So then we talked so much later through the years that we thought we should collaborate instead of keep talking. Well, as luck would have it, we each have a student that are willing to do this project. And so with Harry's guiding light, we work on the theory and experiment of guess what? The L gas, the IN gas, and the gallium arsenide heterojunction. So at that time, the modulation doping is very popular. I don't need to explain it to you that the doping in the conducting channel is not a great idea for the conductivity, right? So the fact that the Bell people started by doping it in the junction, in the barrier rather than in the channel will be a good thing. So this particular wrinkle is that people then start making what they call delta doping. Well, it's not quite delta, but it's pretty thin layers of doping. So, so Harry, we should see how well that will work for the channel. So the two things that the experimentalists are going to measure is basically the Hall effect, the magnetic field dependence, and then the current density, all that you can get from the Hall effect, right? And then they say, well, let's put a barrier than in the outgas, which is away from the channel, which is in gas. And then you have a delta doping source for the carrier. And then you measure the carrier density as a function of the doping. And so those are the two properties. So the second property is the resistivity tensor that you can measure. So that gives you a lot of information, such as the saturation from the DX center and what is the second one? And basically the current resistivity effect. And then you can do the, so Harry said, well, why don't we make a delta layer in the outgas, and another one with the with a very thin layer of pure gallium arsenide surrounding the impurity doping, make it a little bit better maybe. Sure enough, it did. It kind of really raised the saturation current, saturation density, and make things a lot better. So Harry and I had a great time. Well, I hope Juan and Mohammed did too, but at least they got their PhDs out of it. Eh? So Harry and I were fellow inmates in CCRC. If you're too young to know what that is, it stands for the Continuing Care Retirement Communities. So our place is called V. So Karen Karbanoff, Professor Karen Karbanoff, there you are. It's not too bad, is it? She got invited by Harry for dinner and bringing a student, and Harry said we should join them. Then, then something happened. He had a cold, so he said I should host it. So I marched the two ladies up to the fancy dining room where Harry already made the reservation. And they said, oh, I'm sorry, you can't come in. Well, I forgot, and Harry forgot too, absent-minded professor, that they had a dressing code. One or two of our guests were wearing jeans. That was a big no-no. So, but they say, oh, Dr. Sham, we'll get you a nice table downstairs. You can go there, which is more relaxed. We had a great time, especially Karen's student. She said, well, it's so much freer to talk and so on and so forth. So I hope we have forgiven Karen. So around, it's in the fall of 2005, my wife and I started looking for places to retirement communities. So we were the V looking for the apartment. Things look very grim. My wife doesn't like this one, doesn't like that one, and so on. So I say, oh my God, how long is it going to take? And then Harry came along and saw us and said, hey, you should move in here. It's a great place. Well, that kind of, I think, has some influence. So we got there finally. And so we arranged to have dinner on the first Tuesday of every month. And we did that, let me look from my calendar, we did that from April 7, 2015 to May 3rd, 2016. Then in June, I think I jinxed the whole process by not being able to attend the first Tuesday, so we arranged for the second Tuesday. Then Harry, just a couple of days before that, he said he was sick, couldn't do it. He was having trouble swallowing food. So he said, let's do it another week, the second week. But then by the second week, he just couldn't make that. So that kind of stopped the regular dinner that we had. But I have to tell you the dinner, why that was so important. Because every dinner, there was only the two of us, right? Only works with only two of us. He would bring a paper. He said, oh, this is the latest, you know, Harry, very excited. The latest discovery of what materials the things can do. And so we started talking about it, and I always tried to just sort of slow him down and say, well, this won't work. So we had a lot of fun with that. And and then what happened after that was that I think the first year, he was just, I saw him very few times, but we kept in touch on email. He said, well, he was finding it a little difficult, so he wants to take care of his health, and then we'll get dinner again. Then the next year, that is, I guess, between the summer of 2016 and, no, the second year will be 2017 and 2018, he said he actually had problem with his esophagus, and he could only eat very bland food. So of course, being Harry, he wanted to cook it himself. He designed the cooking. Fortunately, his son and daughter-in-law helping him to get this healthy food that he could eat. Well, I really miss those dinner conversations. Thank you.
Yeah, thank you very much, Lu, for a very touching story about Harry. So our next speaker is Dave Harry, professor of electrical engineering from Arizona State University. Yeah. So.
Yeah. Without falling on my face, which happens sometimes, which has nothing to do with being unstable. So, most people recognize Harry from this. I had the fortune of coming to San Diego 2 to 4 weeks each summer when I was part of the Defense Science Research Council. And Harry would always take the opportunity to say, let's go sailing, which would lead to 2 hours or so of nice talk on scientific topic of the moment in Harry's mind. But apparently Dora didn't like to go sailing with him, so he only went sailing when he had friends in town. Is this one working? Or?
Oh, I don't know.
This one was working.
That's a laser.
There was,
Yeah,
this one.
okay. So that's a picture of me sailing with Harry one day out on the bay, and so we had a lot of fun that way. Harry's career, of course, started before this paper, but this is when he was with Naval Ordnance Laboratory in Corona. The importance of it is that he uses indium antimonide. And I started on indium antimonide in 1963 and had several papers on that. And so this was kind of a material that was between Harry and I for the next 50 or 60 years. Because we both had significant early days of indium antimonide, and we always kept coming back to it too. Harry would just lead us back to that. And so he went from Corona to San Diego when the Naval Ordnance Lab was combined with its other half in White Oak, Maryland. And so he didn't want to go to Maryland. In addition, he published this book about 1970, and if you look at the book, about 20% of this book is on indium antimonide surfaces and interfaces. So it remained an interest to him with his love of indium compounds. So it was interesting for us. In it's coming up here. In 1979, you saw Carl Wilmson's name. I went to Colorado State from O&R in 1977, and so in the next 2 years, Carl Wilmson and I convinced the administration of the university that Harry should get an honorary degree. Now, his talk at their ceremony was a creation of creativity. This is one of the lines from it. I'll let you read it because it always cracks me up. But it's an interesting thing, and especially in the politics of today, it's a very meaningful line. It's very important. We should think about things like this a little more. But in the following years, even after I left Fort Collins and went to Arizona State, Harry was a collaborator of ours furnishing material. Right? And so we had a lot of stuff here, and it furnished us indium arsenide on which we grew oxides, and we could make nice devices out of that. And then the three ternaries as well on materials such as this one right here. Right? Lateral surface superlattices, where we were using electron beam lithography, and Harry was always interested in what we're doing there. This continued in the years. This is already 1996. Again, he's giving us indium gallium arsenide. So he was growing the material for this, and he would be very interested. Some of the time on the sailboat was talking about what we were doing with the material and how it was working. But one of the interesting things about Harry, he didn't just put his name on the paper. He had to understand what you were doing. And you couldn't send the paper out till he knew exactly what you were doing. You had to have it. Now, the year after this, I had in the spring of the year an option to spend several days on the Uss Stethem. It's one of the early Burke class destroyers. And I put it in here. Most of you don't know, why is this in here? Well, I was sitting and talking with Harry not a month after this, and he says, oh, that's the ship. I thought he said son, but I'm sure it was probably grandson given the years difference served on. Said he spent time on this ship. And I thought, okay, I can't get away from Harry even by going to sea. And then again, I'm with Harry a couple of years later. This was the end of a 10-year program, the Frontier Research Program in Japan. And Harry and I were on the evaluation committee who was supposed to come and write the final report. So it's one of the few times I can remember Harry really taking a long trip to Japan in particular. So he keeps showing up there, and because he knew what people were talking about. He had always had that effect. And again, when I came back, more materials. Now we're doing heterostructures. Harry is providing the material for us, and we continue to work on this. And you get the idea, we collaborated for a long time, a very long time. And he was always, you know, all the years I've known Harry, since started back in '73, I don't think I've ever seen him lose his temper. He would always have a discussion and say, no, wait a second. Or have you thought about this? Always the case in a nice civil manner to keep the conversation going and describe things that you didn't really think about. Now in recent years, like the last couple of years, I've been working on what are called hot carrier solar cells, which tends to mean that people are not making the solar cells the way I think they ought to make them, right? Because we would like to use these satellite valleys as metastable levels and then not lose so many phonons. And the idea is to use a material like indium gallium arsenide, a material of great fondness for Harry, and aluminum indium arsenide is another material which he was very fond of. He kept saying to use it. And the idea is that we want to bring the carriers out from the L valleys, not from the minimum of the conduction band. Now the problem is, we know we've broken the band gap rule because we get a open circuit voltage of about 1.3 volts. We don't get a good fill factor though. We get good current. If we could get the fill factor up, we would probably be something near 50% efficiency. Now the problem is finding this material that has the L valley at a minimum and has a reasonable band gap to make it all work, because there's a tunneling barrier we have to get rid of which stops the fill factor. So in preparing for this talk last Friday, I'm trying to find a picture of Harry on the web, right? And somewhere in there, I don't remember where, there's a link to a paper by you and Harry on aluminum indium arsenide and DX centers. Not aluminum indium, yes, aluminum indium arsenide, DX centers and aluminum indium arsenide, right? And in there he has a band gap versus composition, right? And sure enough, at about 30% indium arsenide, the L values are right where we want them and the band gap's about right. And I've got, this was last Friday, I've got this feeling Harry's reaching a hand out from the grave to tell me this is where I got to go. So he's still influencing what we do, even now. So I will leave you with the picture I did find on the web of Harry, and he doesn't look much different than he did when I first met him in 1973. So thank you for your attention.
Yeah, thank you very much, Dave, for talks about his early days. So now our next speaker is Karen Kavanagh, professor at Simon Fraser University in Canada.
Thank you, Charles. Lovely to be here. I really feel like I've come home because it's so many familiar things, although there are quite a few new buildings and the coffee is different. However, this is trying to give you a flavor of what it was like to have Harry just down the hall from you to talk to any time, because he was, most of the time you'd find him in his office. And he was always open. It was an open door policy. You could talk to him about whatever it was that was bothering you, or maybe about that proposal you were working on with him. So over the years I was there, I went to UCSD in 1989, and over the years I had these students working with me. Probably all of them sat in Harry's office being mentored in some manner that I didn't know about. But the primary ones that we collaborated with, Jessica Chang, and later on, Rachel Goldman. So I think you'll hear more about what Rachel thought later. But I am going to try to focus on, this will move forward. How does this, oh yeah, just a picture of approximately what I looked like back then. This is a little later, but you see my office is more of a chaotic state with organized chaos. But if you've ever been into Harry's office, it was devoid of clutter. It was very organized. And that was one of the pleasures of going to his office, because I could leave this chaos and sit in a calm environment with somebody that never seemed to get upset about anything. That's how that was one nice thing about Harry as well. I think Lou Sham already alluded to that. But around the office were other people that I had to deal with. For example, these two, SS Lau, just next door, and Peter across the hall. I think you'll hear from Peter later. And then that last office, who lived there? No, not Charles too, but Charles was just around across down another corridor, not too far. And his student, Patrick, was heavily involved with some of our collaborations back then. But the person I'm alluding to was Bill Chang. Bill Chang, he was in that last office, and he kept us all together, I would say. I think this occurred at Bill Chang's retirement, but I'm not sure where I got this picture. Somebody might, is that right? But Harry was there. You can see him with Dora and Bill's wife and a bunch of us. Okay, So when did I first meet Harry? I was trying to think about when I first encountered him, and I think it was at a PCSI meeting. Physics of Compound Semiconductor Interfaces was the original name, and I think he was one of the originators of that meeting back in the late 70s, perhaps. And these were a bunch of people that were fascinated by these compound semiconductor interfaces. There's an example of gallium arsenide, and could be a metal contact, or it could be another semiconductor. Whatever it was, there were problems. And maybe even you can tell what problems this one had. It was it looks like a serious oxide problem, and it wasn't very smooth. And silicon was way ahead. It was taking over. And so the problems associated with these interfaces were fascinating because they also offered better ways to make many of the devices that we were interested in. So we would meet at these meetings, about 100, 150 people, and discuss issues. Now, Harry, as you've all heard from Dave Ferry, was way ahead of everyone in understanding where the problems were. And he'd already thought about it, and he'd worked on one of his favorite materials, indium gallium arsenide, and he knew that the surface barriers change. So the barrier to getting charge in and out of your device is important to controlling your conductivity and emission. And so Harry was driven by trying to harness the properties of these higher indium composition materials because they had better properties than, of course, gallium arsenide's wonderful, but it's not as good as indium arsenide. So that was one of his strategies. And I joined the group there with some background in defects. Defects such as impurities and crystalline defects often will control how well your device works. And these were easy to see. You can see them, obviously. These are dislocations. They're having a big effect on the stress in the material, as well as strain and where the impurities move. And Harry was interested in increasing that indium concentration, yet it would introduce strain, and that would be a problem because you would generate dislocations. Dislocations weren't good for electrical properties or optical properties, but I liked them because they were easy to see. Another thing that's easy to see is precipitates. So here's an example of silicon diffusion. Was something I worked on as a graduate student. Silicon is also important to changing the conductivity of gallium arsenide and other compound semiconductors, so it would diffuse and get stuck in arsenic precipitates in this example here. So you had to make sure you controlled the stress as well as the impurities that you were adding on purpose to control the properties. You needed what was called an MBE machine. This is not Harry's MBE machine, but I just took that as an example of the complexity that can come with an MBE machine. And, oh, okay. TRW, there are hundreds of these all over the world, and they usually have a large stainless steel chamber that has to be maintained at low vacuum without impurities. And if you're as fastidious as Harry was, you had to be really careful what you put into. Here, just a minute, I am going ahead of myself. Wrong direction. Bottom, go back, back, back. This is more like Harry's. I couldn't find a picture of Harry's chamber. Maybe some of you have one. It's a nice, smaller research type of MBE machine, and you had to really be careful what you let into it because that would change your device that you're trying to make. But let's see what's next. This is what Harry produced in the end from growth in his carefully maintained MBE machine. These are, as Dave Ferry alluded to, an interface between two ternaries that give you some very interesting low temperature properties that Harry could measure. And meanwhile, how did you do that? You grew the material in this perfectly maintained system, but you grew them on a slowly changing indium concentration. You increased the concentration in steps, and this was a picture showing, obviously you still have dislocations, but you've reduced their density at the top. It's hard to see maybe, but the indium aluminum arsenide, at the top layer is where your device is. And as long as there's no dislocations there, everything's fine. And hence, this is one of our first joint collaborations, a combination of measurement of the device property with the structure that was allowing this to happen without too much degradation from those defects. So we were controlling the structure while we measured very high quality electronic properties. So this is electron mobility. How fast can you move a carrier through your material before it gets scattered? Or this is important to your cell phone. How fast does it work? What's the bandwidth? Gigahertz was what people were looking for. And I think they still are trying to increase to terahertz, etc. Meanwhile, we are looking at the beautiful dislocations. And dislocations, for me, were more interesting than the, okay, yeah, you can modulate it, yeah, and get high frequency, great. But this was causing some interesting tilting in the material. Maybe we could harness this. And there was some asymmetry in the whole process. You can tell those lines are not the same density in both directions. And this is the X-ray diffraction we could also harness to tell us the bulk material. And, well, you'll hear from Rachel, who's another student that took this asymmetry and worked on a thesis to do with that. And this is a picture, probably, I don't remember where this was taken, maybe at a PCSI. Does anyone remember? And there's some Patrick and Jerry Woodall, Harry, Rachel, and Plug from Germany. And this was another great meeting discussing the same issues. And also, meanwhile, there were other students in my group, and some of them did graduate. Here's quite a few of them graduated, I think. Here's a party, and I don't think Harry was at this party, but a lot of the other students and faculty, some of you may know, were there. I think it was Ken Ring, but I'm not sure who was graduating. Do you know who graduated? Oh, was it my 10-year party? Oh, okay. So it was even more important, I guess. I was going to maintain my job and allowed to mentor some more poor students. And then there were other parties. You might recognize some people here. Maybe Harry is one of the ones in the costumes. However, we did have fun, and I was in charge with Chris Vanderwall of organizing the 1999 PCSI meeting, which we had in San Diego, and I can't thank Harry enough for all his great discussions. And I am getting very teary, but I had to leave in 2000, go back north, and we continued emails, but it was tapering down after that. But thank you, Harry.
Yeah, thank you, Karen, for a moving speech. So our next speaker is also a former colleague like Karen, is Ed Yu from University of Texas, Austin.
see, so is this the advancer? Okay. All right, so thanks very much, Charles. It's always a pleasure to come back to San Diego and have a chance to reconnect with so many old friends and also meet some new ones as well. So when I got an email from Charles and he asked me to come and give a technical presentation for this symposium, what I thought I would try to do is to take some of the research interests that Harry had very early in his career and connect those to some of the topics on which we worked together when we were together here at UCSD, and then connect those to some of the things that we've been working on over the last few years, in which Harry and I had a chance to discuss when we saw each other within the last few years. And as hopefully you will see, the idea of phenomena related to dielectric polarization in materials provides one thread that can connect these different areas and eras. So when I was putting this talk together, the first thing that I did, of course, was to go to Google Scholar and type in H.H. Wieder. And the first research paper that showed up is this one over here. Right, electrical behavior of barium titanate single crystals at low temperature. And this paper is really about the behavior of spontaneous polarization, which is a form of dielectric polarization in ferroelectric materials. And Harry did some of the very early work on this. So the second paper that showed up is this one, all right? And this is a paper, it was a collaboration involving Peter Asbeck, Harry, and myself on group 3 nitride heterostructure field effect transistors. And Harry had some really great insights into what happened with defect and trap levels and such in these devices. But it turns out that in these materials generally, this idea of dielectric polarization, spontaneous polarization, and piezoelectric polarization also plays a very central role. And I'll tell you a little bit more about that in a minute. And then almost exactly 2 years ago, I had a chance to have dinner with Harry over at the V. So Shadi was very kind to help arrange this. And we talked about a number of different things. We talked a little bit about some of the research that we were doing now. And one of the things that he was very, I think, pleased and also surprised to hear was that we had actually been able to involve a number of undergraduate students in our lab in really meaningful research in solid-state materials and device physics. And I think he felt that that was a very challenging thing to do. So I'll tell you a little bit about some of the research that we discussed on that day, and that also ties into this idea of dielectric polarization, and also had one of our undergraduate students very closely involved. So if we go back now and look at this area of group 3 nitride semiconductors and how that ties into this idea of dielectric polarization. All right, these materials, as many of you probably know, are really the foundation for modern solid-state lighting technology, for lasers and Blu-ray players, and also increasingly for certain types of high-power electronic devices. Okay, and the basic structure of the field effect transistors that were the subject of this collaboration with Harry is shown over here. So you have a thin layer of aluminum gallium nitride that acts as the barrier, and then you have a gallium nitride channel, all right? And it turns out that in the nitride semiconductors, because they have the Wurtzite crystal structure, you can have a non-zero spontaneous polarization, all right, as shown here. And also when you have layers under strain, you have a very significant piezoelectric polarization as well, all right? And what happens then is that in a heterostructure like this, you have these two different materials with an abrupt interface between them, right? The two materials have different polarization fields. And so if you think about what happens if you were to put two dipole moments of different magnitude kind of on top of each other like this, if they are different size, then say the positive charges at the bottom of the upper dipole and the negative charges at the top of the lower dipole will not quite cancel out. Right, you'll have some charge that's left over and uncanceled at that interface, and that's exactly what happens here. At that interface, you have quite a large sheet charge density. That's basically an electrostatic charge density. In this case, it turns out to be a positive charge density, and that charge plays a key role in attracting electrons electrostatically to the channel of the transistor and allowing these devices to operate at high current levels and therefore high power levels. Okay, and this idea of polarization, right, dielectric polarization and its connection, in this case, with strain, right, this paper that I've shown here was one that sort of explained the nature of a lot of these kinds of effects over 20 years ago now. And it's really now a central part of how people think about nitride heterostructure devices and materials generally. Now, it also turns out, this was a long time ago now, but it also turns out that these kinds of behaviors, strain, dielectric polarization, and the connection between them, are becoming newly prominent in new classes of semiconductor materials as well. Okay, and I'm referring here to atomically thin, so-called two-dimensional semiconductors, and specifically what are called transition metal dichalcogenide materials, or TMDs. All right, so some of you may be familiar with these. These are basically layered materials. Right, each layer is in these materials 3 atoms thick, and the successive layers are bound to each other primarily by van der Waals interactions. Okay, and so it turns out then that it's possible to separate and isolate these layers down to the monolayer level. All right, and there are a number of interesting things that happen in these materials as you make them extremely thin in this way. The one that is really of interest to us for this talk is the fact that they are extremely flexible mechanically. You can have very high levels of strain, all right? And that strain can be in very unusual configurations. Okay, so I want to talk a little bit about some of the consequences of that in these materials. All right, so again, right, there are many different consequences that these effects, that strain can have in TMD materials. And the one that is really of interest to us here, let's see, is this a, oh, okay. All right, the one that is really of interest to us here is this. That you get some very interesting behaviors in electromechanical coupling, which is the relationship between strain and dielectric polarization. All right, and this takes, for our purposes, 2 forms. Right, there is first piezoelectricity, which is a very well-known and well-studied phenomenon. All right, it's basically a behavior where you have a dielectric polarization that arises in the presence of stress or strain. It's proportional to the stress or the strain, all right? And then you have the converse, which is strain that arises in response to an applied electric field, all right? Now, piezoelectric behavior is governed by a 3rd-rank tensor, as shown here. And because of that, then it is non-zero only in non-centrosymmetric materials, so materials that lack inversion symmetry, okay? And this turns out to be quite interesting in the context of these TMD materials, because if you look at them in their bulk form, you have these atomically thin layers that are stacked on top of each other, and they're kind of stacked like this, right? So each successive layer has an opposite direction. And so if you look at the crystal as a whole, it has inversion symmetry, so it's not piezoelectric, all right? But if you go down to a single layer, a monolayer, you only have this. And this does not have inversion symmetry, or it does not have inversion symmetry, and so it is piezoelectric. So this has been shown both theoretically and experimentally. Okay, and it has some very interesting consequences that I'll talk about in a few minutes. The other phenomenon that I want to point out here is what's known as flexoelectricity, and this is a little bit different. Okay, in flexoelectricity, what happens is that you have a polarization field that is proportional to derivatives of the strain, or in the converse effect, stress or strain that is proportional to derivatives of the electric field. Now, this behavior is governed by a 4th-rank tensor, and so it is non-zero in all materials. Okay, so every material has this, but flexoelectricity is actually a much less well-studied and understood phenomenon, partly because it's more complicated, but then also because in bulk materials and even conventional thin films, it's very hard to get to levels of strain and inhomogeneity in strain that actually make this effect be of significant size. But in these atomically thin materials, because they're so thin, you can get high levels of strain and large strain gradients, and this actually becomes a quite prominent effect. So how do we see these effects? What we do in our lab to study this is we use a technique known as piezo response force microscopy. And what we do here is basically in an AFM, atomic force microscope, we apply a voltage between the probe tip and the sample across the material of interest, right? So that's, whoops. Yep, okay. Right, so that's shown over here. And then what happens is that the resulting electric field or derivatives of the electric field through the converse piezoelectric or flexoelectric effects, respectively, give you deformation in the material, which you can then measure in the AFM, all right? And it turns out also that you can distinguish between piezoelectricity and flexoelectricity because piezoelectricity occurs only in the plane of the atoms, right? So you get only horizontal motion, which gives you kind of torsional motion of the AFM cantilever. Flexoelectricity can give you that or vertical motion. So if you see vertical motion, that can only arise from flexoelectricity once you've checked for artifacts and things like that that can occur. So that idea is basically what's behind this paper here, which was one of the things that Harry and I had a chance to discuss when we had dinner together a couple years ago. And I wanted to highlight this because it brings together this idea not only of dielectric polarization, but also this, what Harry was very interested to hear about are involving undergraduates in research. So this student here, Calhoun Cole, was one of our undergraduates. He played actually quite a prominent role in this work. And I also wanted to mention that this really worked out in large part because of this other student, Chris Brennan, who took it upon himself to be a really good mentor for Calhoun. And I wanted to mention that here because that was one of the things that, as you heard from others, and I think we'll continue to hear from others, that was one of the things that really made Harry special, was his interest in mentoring and advising younger scientists and educators. And in fact, when I was getting ready to join the faculty here at UCSD back in the very early 90s, my thesis advisor, Tom McGill, who I just learned from Charles, came to the 70th birthday symposium. He said to me, you know, you should really get to know Harry Wieder, okay? Harry is a deep thinker, and he has great wisdom and insight to impart. It would be good for you. So, indeed, that turned out to be the case. In all my interactions with Harry, that thinking and insight and wisdom really came through. It was good for me, and I'm really very deeply grateful for that. And I think many of us here have had that same experience with Harry over the years. So, let's see, let me try to move a little faster here. All right, this is the basic idea of what we did in this set of experiments, and the upshot of this is that we were able to show that, in fact, you do see this flexoelectric vertical out-of-plane response. Its magnitude is pretty much in line with what you would predict based on a simple model of flexoelectric behavior, and also it's of a similar magnitude to piezoelectric effects in these materials. So it actually is something, which are quite strong, so it actually is something that is really quite prominent, or can be quite prominent under certain circumstances. Okay, and we've also done this in other TMD materials, and we see similar effects with variation in magnitude over roughly a factor of 3. So now, right, one might ask, okay, is this something that is kind of a materials physics curiosity, or does it have significant consequences for devices that people are trying to make out of these materials? And I think the answer is turning out to be that, in fact, it does have some quite significant and interesting consequences. One of the applications that I think is very interesting here is that people are trying to use these materials to make what are called single photon emitters, right? So they'll emit one photon at a time, all right? And that's something that is very interesting now for applications in quantum information processing, all right? And the way that this is typically done for these materials is that you have a substrate with something like a pillar sticking up. You drape a thin layer of this TMD material on top, and what people observe, this has been seen by a number of groups, is that from the apex of that pillar, where you have the maximum amount of tensile strain, and the combination of that strain and of some defect that is of currently unknown nature and origin, and this is something that I think Harry would be very interested in, gives rise to single photon emission. All right, and in fact, people have tried also to look at the wavelength dependence of that emission and convert that through deformation potentials to a corresponding strain. And if you can, you might be able to read it here. Right, the levels that they come up with are on the order of 0.5% of strain. But actually, if you look at the morphology of these structures and do some simple mechanical modeling, what you would really expect is that the strain is more like 1 or 1.5%, right? Really significantly larger. So we were interested for this and a variety of other reasons in trying to understand, okay, what really is the relationship between strain and luminescence in these kinds of structures? And so we did the experiments shown here, where basically you fabricate samples that have a thin layer of TMD suspended over a hole, and you push down on it with an AFM probe tube. That gives you very precise control over the strain, and then you look at the luminescence, okay? And basically what we see is that, in fact, yes, you do get this shift to lower wavelengths, which is what you would expect, but if you then use deformation potentials to convert that to some equivalent strain, this says that maybe you have 1 or 2%, but the morphology suggests that you should have substantially more. So something is missing in all of this. And of course, what's missing is what I've been describing, this idea of piezoelectrically induced polarization fields and the corresponding potentials. All right, so, and we know exactly how to analyze this from the earlier work that was done on the group 3 nitrides. Okay, so we can take this geometry, figure out what the strain distribution looks like. All right, this is a pretty well-established thing. From that, we can determine what the piezoelectric polarization fields are. And in this particular circumstance, it's likely that piezoelectricity is dominant over flexoelectricity. And then from there, we can figure out what the corresponding charge density is and what the electrostatic potential is. And actually, these turn out to be really quite large, on the order of plus or minus 1/10 of a volt or larger, which in this setting is really a lot and can have very pronounced effects. And basically what happens then is that if you don't include these effects, you get kind of the picture on the left where the carriers, or actually bound excitons, all want to kind of move to the middle and recombine at some correspondingly lower energy. But once you include these polarization effects associated with piezoelectricity, then the electrons still want to do that, but the holes actually want to be localized away from the center, all right, and you know, sort of tens of nanometers away. And so what happens is that you get rapid ionization of the bound excitons, and the luminescence that you're actually able to see comes more from the periphery, okay? And that's exactly what we see. The luminescence, you know, we see shifts that are consistent with maybe 1 to 2% strain, which is what you have kind of out here on the periphery, all right, maybe of order 100 nanometers or so away from the center. And this has potentially very important implications for how we think about the nature and the origin of single photon emission from these kinds of structures. And if one thinks about it a little bit more, then in pretty much any kind of structure that one tries to make from these materials, you're almost inevitably going to have high levels of strain and very substantial strain gradients. And so these kinds of effects are going to come into play in many different circumstances. And for the types of structures that are shown here, I think that Harry, if he were here, would have some very interesting and insightful things to say about what's really going on here. So this is the last slide. So what I have tried to do is kind of lead you through this path where we've gone from some of the early work that Harry did on spontaneous polarization in ferroelectrics through work that we did together on group 3 nitride devices where polarization effects also play a very prominent role, and then to some of the things that we've been involved in more recently that I had the good fortune to discuss with Harry a couple years ago, where we were able to cover not only his interests in science, but also his desire and work in mentoring and advising younger learners and scientists and educators. And on that note, I should point out that any professor will know that all the work in the lab is really done not by the professor, but by the students, okay? And so these people here are the ones who've really done what I talked about. We've had a number of very nice collaborators from UT, and then these were the sponsors that paid for different parts of what I described. So that's what I have. Thank you very much.
Okay, thank you. Yeah, thank you, Ed, for introducing many new concepts. So now we should have a video presentation by Peter Asbeck, a colleague at UCSD.
I wish I could be here to be part of the symposium to honor Harry and share memories and stories about him, but I've been scheduled to give a conference presentation at just about this exact time. So I will try to convey a few things about Harry in this video. Harry meant a lot to me, and he was one of the highlights that UCSD had for me when I moved from industry to become a professor here. Harry was a key member of the Electronic Materials and Devices group within our department, which was quite well known. Harry already had a lot of distinctions and awards when I came, such as the Welch Gold Medal from the American Vacuum Society. I had a chance to talk with him at a small DARPA workshop here in San Diego before I came, and was very impressed by what he had to say. Harry was a pioneer in developing 3,5 compound materials and FETs, and he led the world in making indium phosphide MOSFETs while at NOSC, the SPAWAR predecessor. He further developed the first MISFET structures using indium gallium arsenide, which continues to be the high-performance FETs in the world today. And this was back in 1981, almost 40 years ago. Harry had literally written the book about 3,5 compounds, intermetallic semiconducting compounds, as shown here. This was somewhat earlier in 1970. This was before most of the people in this room were born. And it was before most people in the device world knew how to spell gallium arsenide. He was remarkably prescient, and as such is regarded as one of the critical pioneers in the world of 3,5s. By the way, if you wish to own a copy, the Kindle edition has a reduced price, and with free shipping from Amazon, you can get it as soon as tomorrow. One example of Harry's stature in the community is perhaps provided by this photo, which was taken in Santa Barbara at an informal symposium. Here, Harry is standing in line with a couple of Nobel Prize winners, Herb Kromer and Walter Kohn, and alongside Jacques Pankow, who was really the father of gallium nitride about 50 years ago. Harry was honored with the Welch Memorial Prize, as mentioned, and gave the Welch Lecture, providing an interesting history of FETs and 3,5s. Harry went through a lot of the physics and showed device results, and also discussed some of the warts that the technology still experienced. He thought deeply about these things, and one of the famous theories about the formation of interface states between oxides and 3,5s is known as the Spicer-Wieder theory. Harry made a lot of outstanding devices, but I think the notoriety given to his achievements, as well as for many others in our world of microdevices, is limited a bit by the fact that you actually see the doggone things. You have to use a powerful microscope. Harry was also one of the cornerstones of the EDM group in a social setting. We actually had quite a number of dinners and less formal get-togethers. Here he is with Bill Chang and SS Lau and Hui Lin Luo and Ed and Michelle. Charles does not show up in all the pictures because he was always very thoughtful and took the pictures of these occasions. Harry was also well known as a teacher, and I imagine you have heard about or will hear about a lot of his outstanding characteristics. both from the standpoint of knowledge of the subject, but also his focus on the fundamentals as opposed to incidental details, and his interest in the students and his almost Socratic way of teaching. I later inherited his course on heterostructure field effect transistors, and it was actually pretty hard for me. I had to learn a whole lot of material, although I hope the students I was teaching did not realize this. The personal touch extended to all of his dealings with graduate students, and one memorable occasion for me you may have heard about from Adam had to do with his holding Adam's oral exam in his home when Harry was not able to make it into UCSD that week. Harry certainly left a legacy here at UCSD from the standpoints of research and scholarship and embellishing the reputation of the group, from the standpoint of leading by example and helping students and colleagues to focus on what is important, and on a personal level by his warmth and kindness. Although we miss him, he still has a strong presence here.
Okay, very nice, Peter. So our next portion is the mentees to give a talk. So the first one is Rachel Goldman. The next one.
Okay, so I was told I had 15 to 20 minutes, and if I don't, I can shorten it. I'm going to talk to you today about semiconductor adventures with Harry. And these adventures began in 1991, and they continue today. So what I'm going to talk about is I'm going to start by telling you about my journey to UC San Diego. Then I'm going to talk about something that will be familiar to most of the other alums, which is the semiconductor reading assignments that all of us had when we came. Then I'll talk a bit about the two parts of my thesis, the official part and the unofficial part. And both of these involve molecular beam epitaxy of indium gallium arsenide films and heterostructures. And finally, if I have time, I'll talk about what we've been doing in my group most recently. I had the chance to talk with Harry about some of it, but not all of it. And I know that he would like to hear about it. So I'm going to, if I have time, I'm going to tell you about it as well. So my journey to UCSD actually started in the 80s. Now I'm giving you some verbiage that was an interview that I had with the story writer for the university. I'm not going to read it. I'm going to tell you about it. And if you get tired of listening to me, you can look at it. I first visited the UCSD campus in the 80s in other forms. I was the daughter of a prospective faculty member in physics, and I was later a prospective student, both as an undergraduate and also as a graduate student. But it was in 1992 that I joined the university as a graduate student in the materials science program. How does this work? So it all started in 1991. I received an offer from Harry and Karen to join UCSD's materials science graduate program, which was brand new at the time. And I decided I should come out and visit. So I came out to visit. I had some miles that I could use. And somehow I found a hotel. This was before Expedia. And Harry came to pick me up the morning after I arrived. I was staying at a Hampton Inn. I think it was near Old Town somewhere. Harry came to pick me up, and he took me to the university, and he started introducing me to people. And he introduced me as, this is Rachel Goldman. She is coming to the university in January to be a graduate student with Karen and I. This is how he introduced me. And I thought, I'm visiting, I'm considering. But he repeated it so many times, and I didn't realize that he already knew the answer, that I was coming. So I had quite a nice time during that visit, and he was right. I ended up coming to UC San Diego. Some of the questions that the interviewer asked me is, what is it that made you want to work with him? Well, in a way, you could say I didn't have a choice, because he had decided that I was coming. But I was very interested in this research project, the combination of working with Harry and with Karen, and I'll tell you a little bit more about that in a moment. It was just the perfect opportunity for me. And basically, one of the questions the interviewer asked me was about how did Dr. Wieder shape my influence and shape my interest in my field of study. And so what I want to tell you is I had worked on a variety of different materials before I joined UCSD as a graduate student, but when I began my PhD studies with Harry and Karen, my focus really turned on to the physics of semiconductors. So I'm going to go back. Okay, and I'll quote myself in one of these interviews, and really the opportunity to work with a world-renowned physicist and pioneer in molecular beam epitaxy, that's Professor Wieder, and a card-carrying materials science with significant expertise in transmission electron microscopy, that's Professor Kavanagh. This was an unprecedented opportunity, and I will forever be grateful to their mentorship, which launched my career in the materials physics of semiconductors. So let's talk a little bit about the story of when I came here. So in preparation for my move to UC San Diego, which turned out to be in February, I had done some work with electron microscopy. And how does this work? Does this work? Oh, it works. Very cool. Looking at electrodeposited dendrites. So I had some experience with electron microscopy. I also came with experience in growing some crystals. In this case, they were nickel oxide crystals that I made in a tube furnace with hydrogen bromide gas, which by today's standards would never have been allowed. We had no official safety precautions. But I had also learned that when I tried to make interfaces with this nickel oxide, that they would fall apart because I was using facilities that were shared by lots of people, including those that like to use lead. It was sort of the tail end of the high TC superconductor days where everybody was wanting to make lead zirconium titanate. So I had this opportunity to come to UCSD, and to prepare for my trip, I bought myself a copy of this book. And I was reading it on the plane, and I was very, very excited to join UCSD. So I arrived, and one of the first things I learned about were meetings with Harry in his office. These were frequent. This was part of the tutoring and the learning the background material that one needed in order to choose a thesis topic. And I'm surrounded here by a student senior to me, which is Juan Fernandez, whose statement I'll be reading in a little bit. And over on the right is Alex Young, who I think started about 2 weeks after I did. And these are pictures of us sitting in what might be thought of as the hot seat, where you would come in to talk with Harry about a topic, And usually he would give you sort of an unofficial reading assignment, and I'll talk about some of these reading assignments. And then the way it worked is you would come back and you would tell him about what you had read, and he would ask you questions. And if you were lucky, after a little while that he was convinced that you had learned something, he would sort of take over the explanation. So this was always the trick. So here I am in the hot seat. There are others that were also in the hot seat. Sometimes the hot seat took a different form. Sometimes it was in the labs, and sometimes it was in his home. So here is David Cheskis. I'm pretty sure this was in Harry's living room, having a meeting with him. And here is Lei Shen, who was officially a Bill Chang student, sitting in front of the MBE. And then over here is Cedric, who I don't think we managed to get a hold of. He's in Switzerland now. And this is Cedric sitting in front of the other lab where we did all the electronic testing. And so the hot seat could take various forms. So I promised you that I would tell you about the reading materials. So let me talk now about the reading materials. First part of the sort of reading materials or education materials was this plot. And Harry had a beautiful version of it in a framed color version of this in his office as you walked in. I could not find the color version. I could not find the original version, but we figured out over the last few days that this was made by P.K. Tian from Bell Labs. Apparently it's unpublished. And this was sort of the map of the world of compound semiconductors. This plot was made in 1988. And this was sort of the beginning of my adventures with semiconductors. Like in this picture, the artwork in Harry's lab office. So here we have a plot of the energy band gap versus the lattice constant. The lattice constant is a manifestation of how close together the atoms are. And everything at this time that we were interested in, we as the community, were materials that took on the cubic structure. So the lattice constant was the side of the cube. And that's all that mattered at that time. We had materials on this plot. These are all compound semiconductors, binary compounds, meaning two elements. The lines connecting the dots are the alloys, mixtures of those compounds. And the ones that were solid lines were direct bandgap semiconductors, and the ones that were dashed lines were indirect bandgap semiconductors. Many years ago, when I went to visit Hadass in Israel to give a talk, on my way out, I had this as a slide, and the security people, two of them, sequentially asked me to explain the solid lines and the dashed lines. I thought for a second that perhaps they had been informed by Harry that they should quiz me. But I realize that they just know what to ask. So in this plot, the most important thing for my life in the 90s was gallium arsenide, and then moving along this line down to indium arsenide. Because as we heard, Harry at the time was very interested in moving to indium gallium arsenide alloys for high-speed electronics, in part due to the changes in the surface barrier, but also in part to the huge increases in electron mobility. So I want you to remember this picture in your mind, and now I'm going to tell you about the reading assignments. So the first reading assignment was about semiconductor surfaces. And this book was the first assignment. Harry gave me his copy of it to borrow and read. Evidently, the book that I had purchased on my way out to San Diego was considered to be too sophisticated for me to start with. So the first assignment was to read this book and derive the surface barrier, okay? And to this day, I still have my original derivation, and it has turned out to be quite useful because I use it in my lectures. The same original version that I prepared as part of joining the hot seat. So I'm showing you something that I stole from the internet, which has a nice diagram, but for fun, I'm gonna also show you the things that are parts of what I sometimes draw in class using my iPad Pro. The writing's not as good, but basically I had about 10 pages worth of handwritten notes to explain this to Harry. He, of course, knew it already, and I'm not going to go through this, but this is the whole depletion approximation. Okay. Now, the second reading assignment was about the Hall effect. And here are a few of Harry's books about the Hall effect and his favorite article from Scientific American, which focused on the quantized Hall effect. Harry also had a beautiful color framed picture showing some aspects of the density of states for low-dimensional systems, which I could not find on the web. But the important thing that he was most excited about at the time when I arrived was the quantum Hall effect and the opportunity to achieve the quantum Hall effect in all sorts of other alloy systems because of these two-dimensional electron gases for their opportunities for high-speed electronics. But we needed to learn about the Hall effect. And so this was Harry's favorite diagram from that Scientific American paper. This is something I've edited because I use it in just about every course that I teach. So I wanted to show you that it's part of his legacy. So the Hall effect and the quantum Hall effect were important ingredients in the reading materials, as well as the surface barriers and the 3,5 compounds. With those under my wing and the appropriate convincing of Harry that I understood them, I was allowed to move on to my PhD project. Now, for my PhD project, I really had two projects. I had two advisors, and one part of the official project was the part that was supported by the Office of Naval Research that was paying for my stipend. And that had to do, as Karen discussed, with modulation doped heterostructures grown on graded buffer layers. And when I started this work, I immediately noticed several things we were doing in the lab that I had questions about. And this led to the side project. The side project were thin films of single layers of indium gallium arsenide. And I worked on these two projects simultaneously. And as you can see by the way I've laid out this slide, this is at graduation a few years later. This side was Harry's favorite project, and this side was Karen's favorite project. And they both liked both projects, and I tried to keep up with both of them as much as I could. And so I'm going to show you a little bit about some of the publications that resulted, first from the official project, in case Harry's listening. And the official project was, as I said, about compositionally graded buffer layers. And we had some good fun with this. We looked at modulation-doped structures that we grew on gallium arsenide substrates using step-graded buffers. Now, at the time, we could only do step-graded buffers because we had to use our hands to increase the substrate temperature. We didn't have the computer control that was needed to do the linear graded buffers. And so Harry arranged a collaboration with some folks at Hewlett-Packard who had these fancy temperature controllers that allowed us to do the linear grading. And so this second paper involves a collaboration with Virginia Robbins at Hewlett-Packard. And in this case, we were able to compare both linear graded and step graded buffers and look at correlations between the strain relaxation modes and the transport properties of these two-dimensional electron gases. We also included in this work, Karen and I spent some time over at Brookhaven National Lab studying the strain relaxation, which at the time we could not easily do with the laboratory source of X-rays that we had over in EBU1. Now let me tell you about the side project. The side project was about studying indium gallium arsenide layers on miscut substrates. And for this work, we had a couple of different papers that came out in our favorite journal of the time, Applied Physics Letters. And we looked at anisotropies in the structural, electronic, and optical properties of films grown on substrates with different densities of steps. So we were all very excited about this, and we could look also at the strain relaxation modes. Now, things have changed since we did this work in the late 90s, mid to late 90s. And the world of semiconductors has expanded. So now, when we look at the world of compound semiconductors, the part that we had when I first started is just this little small region. Most of what we were doing, all of us at that time, had very little to do with visible light, and it had very little to do with traditional semimetals, where the band gap is thought to be closed. At the time I graduated from UCSD, there was some hope. Some demonstrations of doping of gallium nitride had finally been achieved in Japan, and there was interest in combining gallium nitride and gallium arsenide to cut through that visible range. Well, it turns out that didn't work. And it turns out that actually one could combine nitrides with arsenides in such a way to access this lower energy range, which is the infrared. And at the time, Professor Tu was working on this quite a lot and made lots of advances. I did a little bit of it in my postdoctoral work. And when I got to Michigan, I started looking at the fundamentals of incorporating nitrogen into gallium arsenide. I figured I was expanding my horizons. As a graduate student, I basically had 3 elements in my life: indium, gallium, and arsenic. And so now I was expanding my world to add nitrogen. And more recently, so we've done quite a bit over the past 10 years or so, looking at how nitrogen is incorporated into gallium arsenide, and the fact that in many cases, a significant portion of it is not sitting on lattice sites. And Harry was quite interested in this because it kind of changed the paradigm of compound semiconductors. What we started working on in the last few years is also adding bismuth to gallium arsenide. And bismuth sits lower down in the periodic table, sort of equidistant from arsenic. It has very different electronegativity, very different atomic size. And the last time I saw Harry, we had nice conversations about the differences expected in the electronic states, with nitrogen interacting with the conduction band, bismuth interacting with the valence band. And we had also, at that time, figured out how to make films of both of these separately. Now, So we were growing gallium arsenide nitride films at relatively high temperatures and gallium arsenide bismuth films at relatively low temperatures. Now, to give a kind of a general reason for why the temperatures needed to be so different, we can think about how nitrogen likes to form a nitrogen molecule. Everyone learns in chemistry about this and how it's hard to break nitrogen into two elements. Bismuth, on the other hand, bismuth you can think of as one of the elements that's used in lead-free solders. And so if you think about a solder, you can think about a molten metal, and you can easily picture what often happens when one wants to grow a gallium arsenide bismuth film. We get puddles of metal on the surface. So we need to use a lower temperature. Now, what we've done in the past couple of years is figure out how to combine these two elements and figure out the growth conditions that make this possible. What's going on here? Okay, so here I show you in my lab we have many MBE systems. We have 3 of them. And most of the work we had done up until a few years ago was in this machine. And we got a new lab and moved the lab over to the new location, and this picture is taken there. And we waited until the very last minute until we, am I going way over? Until we absolutely had to move this machine. And it turns out that by sort of accident, we figured out how to combine these together. And since I'm out of time, I'm going to skip to the punchline. And the punchline is a new plot of, let me get to the punchline. Here, no, here, wait, oh geez, how do I go backwards? I'm going the wrong way here. Here we go. So this is a 2-dimensional plot showing the composition of bismuth versus composition of nitrogen, mapping out the band gaps for this quaternary material, gallium arsenide nitride bismuth. And the reason I wanted to show this to you is it's kind of the modern version of the original 3-5s diagram that we all learned about when we first walked into Harry's office. And unfortunately, Harry was not able to see this. We put it together in last year, June. And it's taken some time to get it published. It's about to come out in our favorite journal, Applied Physics Letters. And I know he would very much like to see it, and so therefore I wanted to share it with you. And I think I should stop. I've talked too much, but thank you very much for your attention, and thank you to Harry's family for sharing him with us at the university and in science, and we miss him very much.
Yeah, thank you very much, Rachel. Harry will be proud. You show this new bandgap versus lattice constant diagram. So now our next speaker is Norman Tien. So he is from University of Hong Kong.
Oh, good. All right. So anyway, today what I thought I'd do is kind of a little bit of reflection of making impact, right, in the technology world, because I think that's something that Harry would very much appreciate. So let me start with a journey. And I think Harry would certainly appreciate how world events can really have an impact on one's lives as well as one's career. And so in the circle portion is the first part of my career, which of course started here at UC San Diego. And at UCSD, let me see, I was also working on indium gallium arsenide-based modulation doped FETs. And here are some of the papers that we wrote with, again, some of the people that are here in this room. But going back, I got my PhD in 1993. The Cold War pretty much ended around 1991. There was a big downturn in the defense industry, and it looked like it was a little bit hard to find a job in the 3.5 compound semiconductor area, especially in high-speed, high-frequency electronics. So I did a little shift, and I decided to go to UC Berkeley to do a postdoc and change into the area of micromachines or microelectromechanical systems. And this is some of the work that I've done in my career in terms of MEMS. Started as a postdoc at Berkeley. In fact, while I was a postdoc at Berkeley, one of the papers I wrote had a co-author. His name was Al Pisano, which I think a lot of people here at UCSD know of. And then from UC Berkeley, well, here's actually a funny story. After my PhD, I said I didn't want to go into academia at all, okay? Just too much of it. Kind of like Rachel, my dad was in academia, you know, I've been in academia for a long time. No way. But when I went to Berkeley and then did work on MEMS, it was, you know, fabulous. It was a wonderful experience, and the field was just growing in the 90s. So if you want to practice and play in MEMS, you had to go to academia. So that's why I went to Cornell. And so in my journey, I ended up at Cornell. And at Cornell, developed some MEMS technologies. And of course, at that time, you develop MEMS technology, what are you going to do? You're going to start a company, right? So I started a company in around 2000 timeframe. And in 2001, there was a whole optical telecom crash. And so here's a little bit of the company. It was AIP Networks. Yuhua may even remember a little bit of this because you were at Cornell at that time as a professor. We raised $10 million back in the in around 2000 timeframe. So this was quite significant. But as I mentioned in the previous view graph, 2001, the whole optical telecom market crashed, okay? There was nothing that we could do. We kind of went into stealth mode for a while, but, you know, the winter was long, and so, you know, company disappeared. It was a hard lesson, and, you know, I couldn't go buy any new houses and drive Lamborghinis. I had to go back to the university, okay? So I went back to the university and ended up starting to do some administration. So when I was back at UC Davis, and at that time actually had a joint appointment as UC Berkeley, but at Davis became department chair for electrical and computer engineering. So it kind of put me on this path in administration. So let me think, this would be around 2006. I went to Case Western Reserve University in Cleveland, Ohio, was the dean of engineering. And there started work on, you know, issues like clean energy. So build a whole new, you know, energy institute. And then 2008 occurred, right? Which was the Lehman Brothers crash, right? The whole global economy went into a downturn. And as dean of engineering, it was tough, right? So not only did I freeze faculty hiring, I had to work to reduce the administrative and technical staff in the engineering school by 20%. We had a huge recurring deficit, which was about 10% of the operating budget. So it was tough. It was really miserable there. Managed to to right the ship, and have things, moving forward again. And this is just some of the stuff that we were doing at Case Western Reserve. It was also the start of robotics. All right, so there was this, interest in robotics. We played in this at Case. But I just wanted to highlight, actually, this is actually one of my favorite quotes that I use quite often, and I think actually Harry would appreciate this tremendously, which is management is doing things right, but leadership is doing the right things. This is a very, big difference here. And I think this is something that Harry quite, would really resonate with. So, of course, because of the Lehman Brothers crash in 2008 and digging, at least the engineering school at Case Western Reserve out of this, I took a look at the situation and thought, higher education in the U.S. actually would take a while to recover, several years. And in many places in the country, it really hasn't quite recovered. I mean, you kind of get back to a steady state, but maybe per capita, we're not really where people were in the past. So I said, maybe let's look for some places where things are more plentiful. And in Asia, we're having tremendous amount of growth. I mean, many people will say that the next 10, 20 years is going to be the era of China and the region. So I decided to go to Hong Kong. I actually made these slides for another talk several months ago. So didn't anticipate what has happened in Hong Kong the last 2 months. But already at that point, we were already entering into the U.S.-China trade war. So things in Hong Kong now are changing a little bit. But one of the things that now at Hong Kong U, we're talking about a lot is digital. And I'll skip through this part of the slide. Again, we're now actually pushing advanced robotics even further. We participated from Hong Kong into the more recent, it's now already several years ago, DARPA Robotics Challenge. And actually, this part is a beginning of also something that I think Harry would appreciate tremendously, which is a more well-rounded engineer or well-rounded scientist. It's not just about the technology. You must really, have a broader set of skills. And in fact, it's not just, as I say, the technical expertise, but be open-minded and adaptive. Be innovative, creative, yet value teamwork. Harry had his talk at Colorado State on the celebration of creativity. Extremely important. And furthermore, I think in a very technology-driven and technology-intensive world, good judgment and social responsibility are extremely important. And it's one of the things I advocate now, particularly for, quote, STEM students, science, technology, engineering, mathematics, is one has to be able to develop good judgment and social responsibility. And it's actually it's the job of the universities to be able to do that. And that social responsibility is not only for climate, sustainability, climate issues, but social media, right? All this fake news, being able to exercise good judgment. And so, some of the things we're then pushing very hard at Hong Kong U are these issues. So openness, vibrancy, creativity. But the world is now actually, from you might say world perspective, actually going through another transformation, which is this digital transformation. Actually, this morning when some of us were talking about things, our students who are getting PhDs in material science are going into data, in material science, going into data science, working for Google, working for, also over in Asia, working for Alibaba and companies like this. So this digital transformation is really taking the world by storm. I was talking earlier that the hunger for data now is insatiable. And because people are now driven by wanting data, and I use an example would be, let's say, the Apple Watch or the Fitbits, where you're generating tremendous amount of data. How many steps? What's your heart rate? Now, it can tell if you're have atrial fibrillation. I mean, all this data, which actually we survived plenty well, plenty fine for decades without any of this stuff, but we want it now. We're paying money for this. And so this will drive data science, and eventually it will come down to creating the new hardware in order to be able to support all of this data hunger. But one of the things that all this digital transformation will do is change our job landscape. There will be new jobs, different jobs, chauffeurs, assistants, co-workers, advisors, AI and robots can either replace or team up with you on all of these things. Caretakers, too, even doctors, right? If you imagine a radiologist looking at an X-ray, right? Today, AI may actually be able to spot, a hairline fracture better than the eyes of a radiologist. So one of the last lines there is, even professors, right? Because actually, in fact, some of the research that historically has been done by professors, which may be more trial and error based, will be gone, because that kind of stuff will be replaced or be better done by AI and machines. So the bottom line, I give a related kind of talk and messages to young students. And what I tell them is, a university student today, you're going to be looking at, maybe another 40, 50 years of a career, right? And I can guarantee you that even within the next 10, 20 years, your lives will be different. Your career options will be different. Jobs will change. So what is going to be of value, what one must take advantage to hone and develop while you're still young, and let's say at a university, is creativity. Because going into the future, creativity is going to be what will be of value. And if you have that, you can work on that, you will remain an asset. So in society. So this is another quote that I oftentimes use. Maya Angelou, a famous poet and writer, you can't use up creativity. The more you use, the more you have. All right, so thank you very much.
Yeah, thank you very much, Norman, about your academic leadership and what the students needs to know. So now next is Cynthia Hansen from Space War. Yeah.
So I want to start with saying that Harry Wieder was very important to my life. He made it better personally and professionally than it would have been without him. So that's without question, and I'm very thankful to have interacted with him, have done things with him. I first met Harry in 1980. I had come straight from University of Michigan as a bachelor's with an engineering, and I loved San Diego, but I was hired at the Navy, NOSC, where he worked, and the first year that you begin there, you begin as a new professional, and you have 4 different tours you can do, and then decide the second year where you want to settle down. And I was in a first tour, and I may have been 2 tours, and I was deciding, I have no idea what engineers are supposed to do. I don't understand what the Navy wants with us engineers. And I thought, what have I gotten myself into? It was getting discouraging. And then Harry had posted something of what his group had done, was doing, and he looked like he wanted some help in semiconductors. And I thought, that's fantastic. That was one of the more interesting subjects that I took. And I remember talking to Art Clausen, who was part of his branch at that time. And I had gotten to know him before working, and because they had a picnic area at NOSC, which is a beautiful location in Point Loma. It overlooks the bay, and we'd have lunch there. And I said, I think I'm joining your group. He said, there is no way. Harry Wieder never hires new professionals. And fortunately, he was wrong, because he hired both me and Janice Veteran in 1980. And he was wonderful. He would put us, I guess, in a hot seat. I didn't realize that at the time. But he took the 2 of us and gave us personalized tutoring in semiconductor physics. And I learned about the Fermi levels. I learned about band gaps. I learned about modulation from him. We would just have private tutoring sessions because he needed us to understand the basics of this. And he was very clear. I just loved it. I think if he told me to read a book, I'm certain I would. I was so excited to be somewhere that was so interesting. And he had built up there a lab. He had both the material growth by LPE and by MOCVD, which was created by Art Clausen, who was very good at putting things together. I think because he came to UCSD afterwards. And he had characterization going on. He was very strong in the magnetic characterization, as you've heard from several people. So we learned the Hall effect and so on. We learned to do optical characterization, and we learned a bit about just prototype devices to get some device properties. And the group we had was wonderful. It was managed. People were very happy. And I remember asking him at one point, how do you do this? How do you persuade people in your group to do things? It's just working so effectively. And he said, I don't convince them of anything I don't think that they would really want to do. I genuinely believe what I'm suggesting is what they would like, and I just point that out to them. And then usually that works. And I thought, it's among many wise things that he told me, and I think that it worked out beautifully. People worked together. There wasn't the antagonistic kind of management going on there at all. So he was wonderful to work with there. So fast forward to when he retired. He retired, I don't even remember when, but he was hired by, I think, Bill Chang as a professor here, and he was excited. And I just coincidentally was looking for graduate training. And the program that they had at the Navy at the time, I applied for and got for graduate assistantship, so you could spend time and do work. And so when I went, I naturally asked Harry if he would, if I could be part of his group. And he said yes. So it worked out perfectly there as well, because he knew the Navy interests. I could work on something that the NOSC was interested in. And it went well. I think I may have been the first student of his, although I'm not the first to graduate. Jim Roach, I think, beat me, so that little guy. He's not here, but I was upset at the time, but it's all a good time. It came. Let's see. He was he loved to have intellectual discussions. He really encouraged it. He did not mind if you disagreed with him. That was not a problem. In fact, he liked that. He wanted to hear that. He was very encouraging. I do remember he would come in after a weekend and say, this is the new thing we should do. And I couldn't disagree with him, but I kept thinking, how is this going to come together? When is this, am I going to put this all together as a thesis? But he had all the parts there. He created the same kind of arrangement where he had the material growth that was going on, he had characterization that was going on, and he had device work. My work was in indium, aluminum arsenide, indium phosphide. It was heterostructures where the insulated gate, instead of being an oxide, would be the wide bandgap semiconductor. And we were kind of grappling with, how do you think about these things? How much of the oxide theory can you apply? And it turned out it was a great deal. So we would go to conferences, and he was very open to introducing us to all of the people that he knew there, and that extended our ability to work outside of the lab or wherever we ended up being, and that was very useful. So he was very pragmatic and down to earth, but very eloquent. I remember still, I'll never forget this, that he finally said, "Okay, Cindy, go ahead and try to, begin your thesis writing. So, give me your first draft, your introduction." So I gave an introduction to him, and I was waiting for the feedback, and his feedback was, "This is about as exciting as putting your hands in cold, dirty dishwater." I thought, oh my goodness, this is going to be tough. But I was not put down by that. It was just, we need to work on it. And we did, and I got to the end, and I graduated. And I remember at the time when I graduated, he said, "Cindy, you should think about teaching. You should think about an academic environment, because I think you'd be good at that." But at that time, I had one little girl, an infant, and I was working at it had changed from NOS to SPAWAR, and I had a job, and it just, we had a home, and it just didn't seem like a possible thing at that time. But I'm going to revisit that in a bit. So then I go forward. So post-graduation, I'm still in San Diego, Harry's still in San Diego, and Dora. And we'd get together. I learned that he had a very strong family value. He was very close to and supportive of his family. And I think that he took many of the graduate students on as almost an extended family. He would invite me and the little girls, my two little girls, for tea parties. And we met Dora, who was just another wonderful person. She would give us, we would have tea parties, and we would have trays of cookies, and then she'd have STEM glasses with juice in it for the two little girls. And we'd talk about current events. We would talk about history. I mean, Harry, he was just very intellectual. He liked intellectual conversations, and his way of talking about history was just very engaging. He had a good grasp, and it was wonderful to hear his stories. He loved his family. I remember seeing pictures of the grandchildren. We have one here, Rachel, who, when they were little, I think year by year, there were 8x10s of you every year, you and your sister. It was so fun to watch. And then he was delighted when Becky and Daniel came and could come to the home and make a move from where they were, and then he could move to the V. And I know you know this, but I thought that was so fantastic that you could come and support him. And I know he appreciated it. You did a terrific job. And to that end, my daughter got married not too long ago, but Harry was unable to come. But Daniel and Becky came in the stead, and they came and watched the ceremony, and I thought that was very touching. He just was quite good that way. I know also that he was close to his family and had regular FaceTime conversations with them. And I actually ended up having a FaceTime weekly conversation with him as well, which I loved. We would talk about current events, and I got to know a couple of concerns he had, and one of them, he was worried about how society was going to handle people working in the coming society. As Norman said, we could be replaced, and so what happens then? He was worried about these kinds of things about people. I used him a little bit about Trump. It was very reassuring to talk to him because, I get very upset about things that I hear, and he would be this rational, calm voice, and he'd had a lot more experience, and I thought that's great. And so I don't know if I'm glad that he's not here to see the things that have come, or sad that I don't have him here as well to just keep us in a calm way. But he also had education as a topic that he was constantly concerned with, and I know that he's had that throughout. He felt teaching was very important, and he thought it was harder for professors now because it's known that the incentives to teach is not as great of incentives to bring in money and to bring in research, and he thought that the students were getting a short end of the stick there. And compared to, and I don't know if I have this right, but in my mind, I think he told me that most of his education, all of his tests were oral tests. And so there's just almost no better way in my mind that you can really see how somebody does when you do an oral test. And I wonder if that's part of his eloquence, because he really was quite a clear speaker. But so I'm going to fast forward a tiny bit, that S.S. Lau I don't know why he did this, but somehow he thought of me. The Pruitt School, which is a charter school associated with UCSD, was looking for tutors for their high school students for physics and math. And he thought of me and sent this to me. And I had retired by that time, and I thought, I do have time to do this, but there's two problems that I have. Is one, I don't know how to teach, and two, I don't remember my book work in physics and math. So I decided, okay, you're either going to do something about it, and this echo of Harry saying, think about teaching was still in my mind. So I found a class on tutoring that was offered by Mesa College, which is a community college here, and I took it, and I loved it. I found out that was kind of their feeder into hired tutors, and they hire them. So now I am a state employee. I followed up, and I tutor now, and I absolutely love it. I kind of wish I would have taken action in the past to teach. I find it so rewarding to talk to people one-on-one and learn what they're stuck on and try to help them through that and watch the light bulb go off in their head. I think it's wonderful. And so I'm doing that 3 days a week. At home, I'm like crashing through. I'm almost finished like reviewing all of the physics and statistics and math. And I thank Harry every day for this wonderful new chapter. He's just been a wonderful influence.
Thank you very much, Cynthia, for a very inspiring talk. So now, the last talk before the break, we are a bit late, but so the last talk before the break is Alex Young, another former student.
So I was one of Harry's students from 1992 to 97, and a contemporary of Rachel and Juan Fernandez that Rachel spoke about. Juan was actually my mentor for Harry. One of the things that Harry required was that as a student, one of your responsibilities was to teach the next generation. And so Juan had the responsibility to teach me, and I subsequently taught Cedric and Hussein, who you'll also hear from later. So my thesis work at UCSD under Harry was in 3-5 compounds, as you've heard about. And I don't have as beautiful a slide as Rachel had, but it's kind of the Bible in Harry's lab. And it's the band gap and wavelength versus lattice constant for gallium arsenide and the other arsenide and phosphide compounds. So the work that I did was a follow-up to Juan and Mohammed's work from Lusham's modeling group. And the work was on modulation efficiency. So it was taking delta-doped charge, and how efficiently could you move it from outside the quantum well and move the electrons into the channel away from the charge? And how much did you actually get? And so we had to model that, and we would have to create the semiconductor structures and then actually test it out and run the whole process of building devices, testing them, being on the hot seat and discussing the theory. And then we would repeat this. And one of the major things that I take to heart was what we call that Socratic method that Harry had, which was a deep discussion of each experiment. And there would be a lot of discussion about planning that experiment, the results of that experiment, and what would be the next step. And we would spend hours in his office discussing the science and the technology and how to move forward. And that was his approach. It was deep discussion, constant, in order to make the next step. As part of that work, we talked about DX centers. So the DX centers, you might have heard, is a point defect in gallium arsenide as it moves towards aluminum arsenide on that scale. So there's a critical compound around 20% where the DX center, which is stands for donor unknown. So it robs the channel of electrons and reduces the efficiency of the device. And we worked on a kind of a double quantum well heterostructure as an idea that came about in order to test out if we could surround the dopants with gallium arsenide where this doesn't occur and see if we could improve things. And it was a wonderful learning experience. Just to understand the technology, and you understood by doing and discussion. And based on that work, which was preparation for the next step, and that was, whoops, let me see, and that was here. So we talk about DX centers. Could it be in other compounds besides aluminum gallium arsenide and gallium arsenide? And one of the things you talk about the legacy of Harry Wieder, to me, he was almost like the father of the field. He was there for all of it. And when we discussed in his office what to do, we talked about, again, how would you prove that this defect, which occurs in some other material system, would happen in a different one? And he talked about the duck theory. The duck theory was if it walks like a duck and it talks like a duck, it's probably a duck. And so we went about building these material systems which were invented or made available in his lab through Karen and Rachel's work. This was on step-graded heterostructures. And we built these materials which were not easily available anywhere else. And these were the 30% indium gallium arsenide, indium aluminum arsenide heterostructures. And I listened from Professor Ferry's work, right? And you talked about indium aluminum arsenide. It's not Harry reaching from the grave. It's everywhere. Harry's influence is everywhere, and that's the work that I worked on and Hussein worked on is right here. So Harry's legacy lives on. And it's kind of a development of a personal journey, and out of all of that, the thing that is most important to me is that Harry gave me a job in the first place. And at that point, I came from basic physics, and he had the technology and he had the need for a student, and I was there, and it was wonderful. And so what I want to talk about is what was that preparation for, and where did my life take me? So as Norm said, it's a journey. So what's happened in the last 20 years for Alex Young? So after my UCSD experience, this is my life on a page. I went to Ohio State as a postdoc to work with Professor Len Brolson in his lab, and actually built his lab after he moved from Xerox in the late 90s in surface science. And I'll talk a little bit about that and why I was there. I then moved to a company called Anadigix in New Jersey. So I moved east. You hear, go east, young man, go east, young man, after coming west. And we were part of the cell phone revolution. And I spent 15 years there. In the meantime, I got married and I moved to Manhattan. And it says there, I met my girlfriend in Manhattan at the time. And for 9/11, something we haven't talked about, my girlfriend was in Manhattan at the time. She was trapped while I was in New Jersey. And in 2002, we did get married. And one thing I'll share while I was still working at Anadigix was we were living on the Upper West Side. And every day I would drive out to New Jersey. And coming home, I'm coming through the Holland Tunnel. And every day I'd wonder if the tunnel would be blown up. You got to put yourself back in 2002 and what was going on in New York at that time. And, also a huge part of that experience. I'll talk very quickly about Metrowave, which is a company that I formed during the .com crash. And it was a great time to start a company. I moved back to New Jersey, where I still am today. A big part of Harry Wieder's legacy for me was an emphasis on family and the personal journey. I have 2 children, as you can see, and I'm right now at Broadcom in Briningsville, Pennsylvania, which I'll talk about. So really quickly. So I went to Ohio State for my own personal work with Harry because when we were modeling heterostructures, you had a quantum well, you'd have delta doping, you'd have a quasi-insulator, and you'd have a surface. And when we did the modeling, in my own contribution, what you saw is that the whole thing, and there's like multiple elements to this device. It's a quantum device. It's all coupled. You can't change one thing without changing another. And the biggest variability we found, if you were going to do something in industry, was that the surface was the most variable contribution to that device. And so I wanted to know more about surface science, and I went to Glenn Brelson, who is an expert in that for semiconductors. And when I was there, we worked on gallium nitride, and as you can see, things get more colorful because the nitrides are in the visible range of energy. And we worked on root cause for yellow luminescence. At that time, gallium nitride was full of defects, and there was great need to reduce this luminescence in the middle of the band gap, which was caused by those defects, in order to create a device that would work. And Len Brelson pioneered something called low voltage cathode luminescence for semiconductors. And at low voltages, an electron beam becomes very surface sensitive. And you can use that to induce luminescence, and then you can change the voltage and use it as a depth probe. And we did this all the time, and we created many different research papers on the properties of the surface and the subsurface interfaces, which is Harry Wieder, everything about semiconductor surfaces. So I want to tell a little story about the last time I saw Harry, and that was in 2005. And I brought my wife, who was pregnant at the time with my first child, to meet Harry. And that was a big deal for me. And she got to meet Harry and Dora. And I was all very proud of the work I did on gallium arsenide-based ICs at Anadigics at that time, because we were working very hard to improve the efficiency of those amplifiers. And 1% improvement in efficiency was a huge deal, and could, as in the marketplace, would mean all the difference between somebody buying from you and your competitor. And I was very proud of that. And he told me, you know what, that's all great, but why are you killing yourself over 1%? If you want to increase the lifetime of this phone, work on the battery, for Christ's sake. It's terrible. But did I listen? No. Elon Musk may have listened to him. He was probably there too. So he was that far ahead. I mean, again, you got to put yourself in the time period. So talking a little bit about Anadigics. So I spent 15 years there, and we were pioneers in the application of in-gap gas HBTs. Now, this was not something that Harry built in his lab. This was actually Peter Aspect's work. So this was the competitor. We were FET guys, not HBT guys. But it turns out that this device was ideal as a transistor in use in cell phones. And Anadigics in Warren, New Jersey, had the first 6-inch gallium arsenide fab in the world for analog devices. And this technology was applied, and it's still in use today, actually, for many of the cell phones, the hundreds of millions of cell phones that are built in the world every year. And as a technology, I think it's very cool. We actually, as a company, developed what we called a BiFET structure. So not only the type of PHEM type structures that Harry made, but we combined on one wafer on one substrate, both an HBT and a p-hemp on the same substrate, which had never been done before reliably, and was used in the marketplace for many years. So what did I do? I managed a test lab. So one of the things that I did was what we call qualified multiple technologies and products for the company. So qualification, what does that mean in industry, is a series of tests to ensure that the products work over the lifetime of the product. And the last thing anyone, anywhere wants is for your product to fail after a year in the field. That could cost millions of dollars lost for both you and your customer. And you spend years actually qualifying a technology to get it into the marketplace, because otherwise nobody will buy it from you. I want to talk a little bit just about a company I formed at that time called Metrowave. And I say it, I wanted to put this out there because it was about thinking ahead. And the idea for Metrowave was to bring terrestrial-based wireless internet to the consumer in 2002. Think about the modems that you were using at that time period. So the idea was to use the cell phone towers, which were being built as a base to provide internet coverage in the 10 to 12 gigahertz frequency range, which is where your dish network operates from satellite. But this would be from a tower, and so the latency for that would be tremendously reduced and would be a major advantage to areas with poor coverage for internet service, which is still there today. As a startup, though, you can actually be too soon. People don't talk about that. They always talk about being too late. But if you think about where the space was at that time, we had a very tough time having a price competitive technology that people were interested in, and they didn't even know really what to do with it. But somebody did. There was a spectrum auction. So the government, as you know, sells spectrum for billions of dollars to wireless companies. And for this technology, they had a special auction in 2004. And my startup was outbid by Cablevision by a factor of 10. And they did that on purpose, not because they wanted it, not to build something, which is what you're required to do by the government, but they actually shelved the technology and it's not in use today, just to keep it off the market. And after that, we folded Metrowave. It wasn't, there was no market then for it. But I was still at Anadigix at that time, so life was good. Today, I'm with Broadcom, and what does that mean? We make single mode laser diodes. These are DFB laser diodes, which were actually invented there when it was called Bell Labs. We also make avalanche photodiodes and pin photodetectors for receivers for fiber optics, the internet superhighway. So this is the traditional fiber optics from the dot-com boom as well as crash. And from an industry perspective, this is the original group. And one of the things I was very proud of when I was with Harry was that he had the second MBE machine of its type made by Variant in the world. And the group I'm with now, they worked on the first one. So it's all a very small world. And you can see the legacy here, because this is corporate, how the corporate world works. So this started as AT&T, became Lucent, became Agere, it was bought by TriQuint. They went private, became Psyoptics, and they were bought by Avago. Avago, who's Avago? It's HP. So HP spun off a company called Agilent, who spun off their component group called Avago. They went private equity, they went public again. They bought Psyoptics at that time, and then they bought Broadcom, took the name, hence Broadcom. So, and they're tremendous. This is one company or one business unit out of 23 that they have. So what do I do there? I'm the quality manager there. So what does that mean? Everything produced by that indium phosphide fab in Pennsylvania is my responsibility. So that includes the quality of the back-end contract manufacturers in Mexico and the Far East, as well as customers, keeping them happy worldwide. And a statement I learned actually from someone else at Bell Labs. So what is quality? Quality does not bring you a new customer. Quality keeps them. Think of your experience with any product that you buy. So in summary, family was something very important to Harry, and this is my family. It's on the left, my wife and I when we got married, my 2 kids when they were born, and a couple of photos, recent photos of our family at Taekwondo and in Lower Manhattan, just on vacation. Thank you.
So thank you very much, Alex, for a very nice story. So actually, before we take the break, I'd like to have a group picture, while everyone is sitting here. So we have the photography here. Huh? Okay, yeah, so let's all come on stage.
So Harry was on the PhD.
Okay, good. So let's restart. So first, we'd like to play a video from Hüseyin Sarı, Harry's student, but he is now in Ankara University in Turkey. So he has prepared a video. So can we have the video now?
Hi everybody, greetings from Turkey. My name is Hüseyin Sarı and I am from Turkey. I was one of PhD students of Harry Wieder. I have started working with him from 1996 and I got my PhD degree from UCSD Electrical and Computer Engineering Department in 2001. After I got my PhD degree, I have spent about 6 months in his lab as a postdoc. Then I have returned back to Turkey in the summer of 2001. Since then, I am holding a faculty position in the engineering faculty in Ankara University, Turkey. I am now full professor in the Department of Engineering Physics. Harry Wieder was my co-advisor together with Professor Sadık Asener in the same department, but I have spent most of my time in Harry's lab and interacted mostly with him during my PhD study. In my PhD thesis, I had investigated the excenters in indium aluminum arsenic as a continuation work of Alex Young, who was another PhD student of Harry Wieder. Together with Harry, we managed to add a few more data points on the energy diagram of the excenters in indium aluminum arsenic. By the way, the excenter is a local defect observed in compound semiconductors. It has a very interesting electrical and optical properties. I really appreciate and thankful for Harry for his giving me opportunity to work in his lab. I had a chance to learn much of experimental techniques, including molecular beam epitaxy growing, device characterization, and structural as well as electronic and optical characterization of semiconductors. Harry wanted his students carry out all the experimental steps starting from growing to characterization by themselves, and I was no exception. This experience made me survive and help much to set up some experimental units and carry out electrical and optical measurements on organic thin films that I start working in Ankara University. With Harry, besides regular conversation about my thesis research, we were also talking about Turkey on some occasions. I was very surprised that Harry was very knowledgeable about Turkey. I had learned something new from him about Turkey and Turkey's history. I had invited him to Turkey after I returned back, but for some reasons, I guess he couldn't make it. One more memory that I would like to share with you to show that I still kept learning from Harry even after I had returned back to Turkey. After I came back to Turkey, I was told to write a short review paper on the centers for a journal published in Turkish. I have written a very basic paper related on the centers in Turkish. Of course, I put Harry's name on it. After I sent the paper to Harry, he told me that it was not ethical to write his name on a paper that is written in a language that he cannot understand. At that time, I couldn't realize that it would be a problem putting his name on it, but after thinking about it, I realized that I shouldn't have done it. He kept supporting me even I returned back to Turkey. After 1 year spending in Turkey, I had reverse culture shock, and Harry said that I was always welcome to his lab and work with him. It was very kind of him. Having gained a lot of experience on vacuum, experimental techniques, optical and electronic properties of semiconductors, device fabrication and optoelectronics in UCSD, I wanted my experience to be benefited for Turkish students. After I returned back to Turkey, I wrote a vacuum book together with a colleague. As far as I know, this was the first vacuum book in Turkish at that time. I also prepared open course material about optoelectronics. This was also one of the first lecture materials on optoelectronics in Turkish. A lot of my students and others in different universities in Turkey focused on working in the field of optoelectronics. All this became possible due to Harry Wieder, and of course, not forget my co-advisor Sadık Esener, who made it possible for me to meet with Harry Wieder. Thank you, Harry, for everything. I will miss you.
Yeah, thank you, Hussein. So now we have Kevin Tetz from ON Semiconductor.
How does this thing work? This is going to turn the power off?
That's a pointer.
There. Pointing. That's fine. A little higher. Okay. Hear me now? So when I was thinking about what I would talk about in my time here, I went back through some of my messages, and this is one that jumped out. Pretty indicative of the time that I spent here and visiting with Harry and working with him. So this is an email right after I graduated. The next year is coming back. It says, Thursday is fine with me. I get in about 9 a.m. and will wait for you in my office until 9:30. After that, I will be in the outdoor coffee place, Cups, which during our time, actually, Cups didn't exist. So before that, there was the other coffee place, which I don't know which one that was. Anyways, near the statue of the bear, there, I will be back in my office at 11 a.m. And that was pretty much when we had our time in the hot seat. So All right. So for most of my years, 2001 to 2006, we did meet a few times a week in the hot seat, but it was always after the coffee meeting. Initially, we talked about MBE, like everybody else has talked about earlier, but later, after the first couple of years, it was about pretty much everything else. As the last one, I think I shut down the MBE. So one of the things that I remember about these talks were just Harry's inquisitiveness and his passion for learning new things. That was always, he'd come back, he would have his coffee with his friends, his colleagues, and have something to talk about. And I would always come in and try to give him something else to talk about, something else to think about, something else that he could ponder over for the night and come back and talk about the next day. So the other thing, so inquisitiveness, passion for learning, and he always listened, right? There was always, he would sit and he would listen to me. What did I have to say? So that was something that I always take away and remember. So what did I do for my thesis? I did start with the MBE. So I was growing indium gallium arsenide quantum dots. I was supposed to be using it for quantum information processing. On top of that, I was putting a bunch of small metal holes. And it turned out around that same time, there was some work that people started doing, just looking at optical transmission through those holes. And somebody said, oh, well, more light actually passes through this hole than theory predicts. And so there's a bunch of work on that. Turns out that was some of the regenesis. It's not new physics, but work around plasmonic and nanoscale optics. And so instead of growing the quantum dots, putting holes on it and doing a bunch of quantum information processing through those holes, which is what I was supposed to do, I took a sidetrack and really just studied the physics of the plasmonic effects on the surface of the metal. So anyways, that's what I ended up doing for my dissertation. Okay, so after that, looking for what we're gonna do for after graduation, this was one bit of advice I do remember very distinctly. Don't do a postdoc if you're not pursuing academia. That was pretty much not a verbatim, but paraphrase quote. He was right. I knew it. However, sometimes things intervene. What did I do? I did a postdoc, and I didn't pursue academia. But there was a reason for that. Actually, so my wife at the time, or my now wife at the time, girlfriend, had taken a position that was in Nashville, Tennessee. Nashville, Tennessee was where a company by the name of Nissan Corporation had moved their headquarters, their corporate headquarters had moved to Nashville. And so if I was going to be together with my then girlfriend, now wife, in Nashville, Tennessee, I needed to find a job. And working at the university was about the only job I could find in Nashville, Tennessee. So I did a stint in the Department of Physics and Astronomy. So it was actually cool to hang out with a physicist. I was in engineering before that, but very different perspectives on a lot of things. Anyhow, I did a little bit of work on vanadium dioxide plasmonics, something called coherent anti-Raman, I don't remember what it's called, surface-enhanced coherent anti-Stokes Raman scattering. But that only lasted for about a year. There was a startup out of UCSD by the name of Quanlight. It started, I think, around 2007. Dave Keogh can speak to that. Professor Tu, 2006. Professor Tu would know very intimately about this particular company. It was based in San Diego. There was work done in New Hampshire. I was still in Nashville, Tennessee. Don't ask how that worked. Didn't work very well. There was also a little bit of work in photovoltaics. But basically, we're using a dilute nitride. We talked about nitride devices for the object here was to make thermally stable yellow, amber, red LEDs with a dilute nitride material. I also learned a bit about the law fields out of this. A couple of years later, I was actually part of a lawsuit stemming from this. Definitely a very informative learning experience. We can talk about that in more detail later on if anybody's interested. What did I do next? Actually, so as part of that startup was being acquired or potentially being acquired by a company called Micron Semiconductor. It's in Boise, Idaho. So Boise, Idaho's up there. My little pointer doesn't work. Oh, there's a pointer. It's not as good. So I got this. I thought about this because I had an acquaintance that I was talking to this week from the East Coast. And actually, I've had the same conversation with several people in San Diego. Idaho is potatoes. Iowa is corn. So I moved to Idaho. I've only driven through Iowa once. Anyways, so Idaho, potato, corn. Potato is where I went. All right, so I ended up at Micron Semiconductor. It's a fairly large Fortune 500 manufacturing company, mostly known for memory. They were working on making LEDs. So what we tried to do there was grow gallium nitride on silicon, 200 millimeters. That didn't work very well. It works okay, not great. The other thing is we tried to make a gallium nitride on what was called SOPAN, or silicon on polyaluminum nitride. Basically, it was possible to do this on 6-inch wafers and eventually 200 millimeter wafers. So really, we wanted to use this existing depreciated 200 millimeter memory fab to start doing LEDs for solid state lighting. Really, then at some point in time, there was a takeover of a different manufacturer that took up a bunch of money, and so that program was canceled. So after that program was canceled, I did like Boise, Idaho, and I did want to stay there. So I moved over and started working as a device physicist in 3D memory. So I moved to what is called, or what was a NAND cell group for the development of the first 3D NAND. So I worked on the first 3 nodes. These are pretty, I don't know if you haven't seen these, they're pretty incredible devices. They're huge aspect ratios. Basically, we could get 32, 64, and they're working on 96 and 2x that right now. And these are 2 bits per cell and 3 bits per cell and 4 bits per cell. Right now, you can almost, I think they're available in the market, but you can get a single chip that's a terabit in one chip in your next flash drives. So that's what these will be, these kind of structures right there, with about 4 bits for every single one of those cells. All right, and then a couple years, just about 2.5 years ago or so, decided that memory wasn't going to be the end of my career. I wanted to go do something else. And just down the road, it was actually a spin-off out of Micron, acquired by a company called ON Semiconductor. Alex showed kind of how the progression of those mergers and acquisitions go. And this is, I won't go into the full gory detail, but it was spun out of Micron and then acquired by this company. The office just happens to be down the road. So I started working on pixel technology for CMOS image sensors. So I was a development lead for what is an 8 megapixel ADAS sensor that should be going into production later this year. And next, I'll be working on a couple of global shutter pixels for various in-cabin and for machine vision and a bunch of other applications like that. All right, and so my oblig family shots. So first in Boise, Idaho, we started with 3, a couple pictures there, and then we became 4. And that was, I think, last year right there. And then when I came down here, there's no reason to have these particular shots. It's just when I was looking for this picture right here, I thought those were funny. This is the shot that I was looking for. Basically, I came back to visit, I think it was 2011, and got to visit Harry. And that was my oldest, who's now about 8 years old, 2011. And we had a nice visit, had lunch, and got to chat about all sorts of things, everything else under the sun. And that was it. Thanks so much.
Yeah, thank you very much. A lovely picture. So now the next is Adam Conway and Becky Nikolic from Lawrence Livermore National Lab.
Thanks, Charles. Obviously, I'm Adam Conway. This is Becky Nikolic. We were both in Peter Asbeck's group. At the time, we were at UCSD. We overlapped a little bit. I was there from 2000 to 2006. Becky was there a little bit before that, and I was lucky enough that she hired me at Lawrence Livermore afterwards. Since we're in the same research group, we work at the same place now and have been since graduate school, we figured we'd give a talk together. But so when I was a student, I was primarily walking down that office hallway to talk to Peter, but sometimes I would stop in and talk to Harry, and often got stuck sitting on the hot seat, as people have been calling it, or as I like to think of it, the learning chair. But, and he would give me a paper to read, and I would have to go back and learn it, and then come back and sit down in his chair. What I would try to do when I wasn't quite sure that I had totally mastered the topic of the day is I'd look around his office, and I'd always notice there were tons of pictures of all of his former students. And so, to delay the inevitable onslaught of me failing miserably at answering his questions, I would ask, oh, who's that student? Or what is that guy? I tried to like delay. And so he'd always have some great story about how amazing this particular student was or that particular student was and how proud he was of each of them and all of the, great contributions they would have made to science. And then, get back to, never forgetting to get back to the original topic at hand, which was to give me a hard time about what I hadn't done good enough up to that point in learning whatever the topic was. Of course, in a very gentlemanly and gracious way. And so during Peter Asbeck's talk earlier, you saw a picture of me sitting in Harry's office. So another thing I wanted to do was tell that story a little bit. So, Harry was very giving with his time. And when I was defending my master's thesis or taking my preliminary exam, Harry, Paul Yu, and Peter Asbeck were on my committee. So I was like furiously working to put together my presentation and study all the things I was supposed to learn, et cetera. One time I was like getting obviously very nervous about this upcoming exam I was going to have to take. And, Harry was in his office, and so I walked in to talk to him. So he sat there, and he's like, how's the preparation going? I'm like, I'm trying to do this or that, and I was clearly, struggling or something. And so he's like, I'm going to give you a little tip. He's like, here's the question that I'm going to ask you at your exam. So he gave me a little heads up. So then, time progresses, and I'm about to do my exam. We find out that Harry had, I don't remember now exactly what happened, if he'd fallen and broken his leg or something, but he couldn't come in for the exam. So I was like, well, that's bad for Harry, but yay, I get more time to prepare. And then instead of that happening, though, as you saw, he invited us to come to his house and have the exam in his living room. So I was like, great, okay, I guess this is happening anyway. So, I get in the car with Paul Yu, Peter Asbeck, and we all carpool over to his house and, down, I think it was Point Loma area. And, Peter's from MIT and Paul's from Caltech, and so they were debating on, which textbook was better for which class and like who was the better, professor that they had during that time. And, I was thinking like, man, I don't even remember the classes I took in undergrad, let alone like who wrote the textbook that I was reading. It's like, I am in for some trouble in this exam. So we get to his house, and, his wife, Dora, was there, and she's very gracious, and she had like, refreshments for us and stuff. And so then we walk into the living room, and, Harry's sitting there. He's got his like set up there so I can give the presentation. So I give my presentation, and I think I did pretty good on the actual technical work I had done. And then we get to the question part, right? And so like, first question Peter asked me, I like, fumbled through some derivation on a board, and he's like, okay, I guess that's close enough. And then, Paul, you asked me some other question that was basically on quantum Hall effect, and I think I more or less got that one right, but like, of course I was probably missing a little bit of stuff. And then, finally, like, Harry asked me the question that he had already told me he was going to ask me. And so I thought, like, I had prepared, I had like an answer, and I thought like I knocked it out of the park. And he kind of looks at me, he's like, again, very graciously, it's like, that was close, but it wasn't exactly what I was looking for. And he went on to tell me, thankfully, what he had actually been trying to extract from my brain, which I was not capable of giving at that time. So, I really appreciated the fact that if it wasn't for him and giving me a heads up, I probably would have failed that test miserably, and I wouldn't be standing in front of you now. So another piece of advice that I remember from Harry to this day in my job at Lawrence Livermore as a device physicist is that we heard a lot about how the material science work that Harry had done, a lot of different semiconductor materials. So being in Peter's group as a device person, so his thoughts about device, at least the way that he described them to me, was that devices are a great platform for studying the fundamental physics of materials themselves. And so, we did a lot of work on studying two-dimensional electron gas transport based on AlGaN-GaN FETs at that time. So I still never forget that in my work today, that devices are great and enable a lot of applications, but they're also great tools for studying the fundamental physics of the materials themselves. So thank you, Harry, for that.
I was at UC San Diego from 1997 till about 2002. I was interested in coming to UC San Diego because I was very interested in electronic materials, and I knew I wanted to get a PhD, and I knew I wanted to do research. I knew that partly because I was very fortunate to work as an undergrad researcher when I was at UC Davis. I was very impressed with the professors at UC San Diego. I was eager to start. I interacted with Professor Wieder for a few different reasons. One, Professor Asbeck was my advisor, and I walked by Professor Wieder's office to get to my advisor's office. His door was always open. He was always polite, very friendly, acknowledged my presence, and did have an opportunity to chit-chat with him often. I also took his 232B class, which I think might have been the last time he taught that class. He was an excellent teacher. We learned everything on heterostructures, 2DGs, bandgap engineering, interfaces, and I used all of those pieces of information for the foundation of my PhD work, which was on gallium indium nitride arsenide, HBTs, tunnel collector HBTs, and I worked on a whole bunch of other things. I worked on a lot of different topics when I was a graduate student. However, I've learned so much from him for the academic piece. What I really think about when I reflect on my time at UC San Diego and what I've learned from him is really the soft skills. He was such a gentleman. He was so careful with his words, absolutely incredible. I remember one day walking in the hallway towards the laboratory, and he stopped me, and he looked like he was going to tell me something about physics. He looked really serious, and he, pulled me aside, and he was telling me the great accomplishments of other people and how much they liked science. And that's something that has stuck with me about how important it was to talk about other people's accomplishments in a way that was really endearing. At Lawrence Livermore National Labs, I have spent most of my career developing semiconductor devices of various sorts. UCSD taught me much in the way of very complicated devices and very complex material physics. However, much of my career has been exploiting diodes for various applications. But again, it's the soft skills that as my career has continued and I now find myself in management and leadership positions, how one treats each other is really important. And he was an absolute gentleman and exemplary skills for making people feel good and for lifting people up.
Thank you, Adam and Becky. So next is Patrick Chin from IntelliFE.
Thank you. It's great to have this opportunity to come here to meet Professor Harry's family and so many old friends here. All the previous fellow students and colleagues have made really great speeches on their everybody's experience working with Harry. And I also have a few slides here. How do I? This is for okay, again, no one will be surprised seeing this plot. I joined the UC San Diego Professor Tu's group in 1988, and I stayed for 5 years. Looking at looking back of this group, I think we really are in a very unique opportunity of compound semiconductors taking off or growth. Oh, I'm sorry. Okay, all right. Okay. Yeah, for quite a while, gallium arsenide was considered the material of the future and always will be. Now I think we can say it's no longer the material of the future. I also got this plot from, it was from PK10, but this version was clarified by Franz Schubert. So, when I joined the UC San Diego, Professor Wieder has a gallium arsenide and be taken care of by Peter Chu. And Professor 2 wants to set up a gas source MBE, so we'll be able to grow phosphide. Now, gas source gas, the gases we use is arsine and phosphine. Those are military grade poison gas, really nasty stuff. So when I remember talking to Professor Wieder, he was deeply concerned about the safety of the whole building. but luckily we try our best. I think they are not up to the standard of the current industry safety, but we do our best, and luckily it went okay. So the main material I work on was gallium arsenide and indium gallium phosphide. There's no laser pointer. And then after graduation, I went to Purdue University and did my postdoc with Jerry Woodall. I thought he was on the original plan. Right now he's in UC Davis. So in Purdue, I started to grow phosphide again, but with a solid phosphorus source. So solid phosphorus is still flammable, toxic, but it's not a gas phase, so it's easier to handle. And that 4 years prepared me for a job here in Redondo Beach, TRW. They are trying to grow using MB to grow indium phosphide, HBT, and hemp, and I was able to fit in quite well. So I spent some time over there on and off, totally about 8 years, mainly developing indium phosphide-based HBT and hemp, space qualified high performance product. I think Cindy and Steve Pepper's name came up in DARPA program reviews. Then in 2008, I decided to leave and go back to Taiwan and take care of my aging parents. Over there, I joined the first COPEN and then IQE. Now that's a MBE and a MOCVD epi service company. As Alex said, that a lot of those circuit you call it bi-FET, right? And Digit call it bi-FET. Other customer call it bi-hemp. I got mixed up all the time. About 85% of a cell phone right now has gallium arsenide HBT PA in that. So I've been then last year I decided to relocate back to Texas and join the IntelliEpi. It's a company started in 1999, and we do MBE only. So I take a big detour and come back to MBE production. So maybe we can just compare what we did about 30 years ago and now, how big of a progress this industry have made. And a lot of things now I look at it, can be tied or related to Professor Wider's work in the past, and also most people in this room have done. So at the time in UCSD, these are the topics that are close to our group and Professor Wider's group. Highly strained in-gas on-gas, that's being used on gas PHEM. That's a high volume production product right now. The Indian composition, pseudomorphic Indian composition is between 22 to up to 30% right now. And and at the time we grow phosphide by gas source MBE, and so the product was of interest was indium phosphide HBT or Hong Ho did the highly strained indium arsenide phosphide on that material too. And also Peter Asbach's group did a lot of work on indium gallium phosphide, gallium arsenide HBT. That indium gallium phosphide, gallium arsenide HBT is the main product for cell phone amplifier. But that product is more suitable to be grown by MOCVD. So people do not use MB to produce that. And it's funny to think about when we were at school, we grow samples, the substrates are expensive. We buy 2-inch substrate, and we cut it into 7 pieces. So each one is about the size of my fingernail. If we feel lucky, we grow a quarter piece. We want to go for it, then we'll grow a quarter piece. And right now, both the production MOCVD and the MBE are 7 6-inch platen. So we grow the platens about this big. And each time we can load the seven 6-inch diameter wafers. Or you can load a 52-inch wafer if you want to. Yeah. And then we did some work on fully relaxed metamorphic buffer layer. This will allow people to grow indium phosphide type of device on gallium arsenide because indium phosphide is a lot more expensive. And also currently up till now, 6-inch indium phosphide is very hard to come by. Only one company can provide some sample at an outrageous price. All the customers heard that price and say no. But for the future, okay, this is still up in debate, whether the 5G will go to millimeter wave, meaning 30 or so gigahertz, whether our handset will really need that kind of frequency. It's a good question. We may never need that. But when the frequency goes up, it always will. When it goes up to that frequency, currently we can only see two solutions. That's indium phosphide HBT or gallium arsenide pHEMT. Gallium arsenide HBT will probably run out of gas at about 10 or so gigahertz. Okay. So these are some pictures I took when I was in my first assignment in TRW, then north of Guaman. This picture is similar to the one that Karen just showed. Yeah, that's Todd and Dima. Still remember the name. So this machine looks big, but that's only a 5 3-inch substrate. So it's considered a medium size now. Okay. And then because phosphorus, again, is very flammable, when you open the system, it basically just ignites when it touches the air. So we have to wear that and then do all kinds of a careful thing to keep the lab safe. And even it's an ultra-high vacuum chamber, we don't want water, but in order to handle it safely, we have to basically hose it down with water. So it's a long, tedious, arduous process. But we're able to grow the MBE capability from a small single wafer tool to a multi-wafer tool, so to meet the demand of a production. Okay, so this is 5 3-inch substrate wafer machine. So currently, we are all using much bigger machine. Some pictures are duplicating from Rachel's picture. This is taken in 2003 in a conference in San Diego. I can't remember which conference. Okay. So we have Jerry, Harry, and Klaus there. Yeah. And I remember at that conference, Harry was very curious, just really excited to see some of the souvenirs companies are giving out. Because at the time, the nitride LED is a new thing. So companies are giving out the little key fobs of a bright white light LED. And when Harry saw one, he was just like a little kid, very excited to see that. And I remember that the key fob, I grabbed a few, give it to him. It's made by a company, Amcor. That's where Hong Ho was. So, and this is taken in 2010 when we have a reunion here. And that's Bing and Charles and Professor Chen and also Hong Ho. Okay. This is the company I'm working for right now. That's located in Allen, Texas. That's north of Dallas. That's a new fab. We have an old fab, and this is a new one. Just started running this year. The main fab surface is 70,000 square feet, and we can house 16 MBE machines. Totally. Right now, there are 3 running there because just all the customers are very careful in terms of qualification. Whenever we have a new fab or we move the machine from one side to another, they all require requalify. That's a big headache. So we will be doing that in a gradual way. Now, this company, right now, we have more than 10 Rebaer solid source MBE. And we can grow epi on gallium arsenide, indium phosphide, or gallium antimonide substrate. And we also actually pour the gallium antimonide crystal ourselves and produce gallium antimonide substrate. This is we are one of the two suppliers of gallium antimonide substrate in the country. The other one was IQE. Because we couldn't buy substrate from IQE, they don't sell us. So we have to eventually decide to develop the substrate ourselves. So, and when I was a student, I didn't know much about the antimony work that Professor Wieder did before. But now when we are discussing with the customers on a lot of long wavelengths detector structures, and what Professor Wieder has mentioned about those antimonide work he did just came back to me. So everything seems to just tie together. This is a busy table of the product or the epi layer we are doing in printing in red. The top is the application. But basically, just look at the text in red. These are the epi structures that we grow for our customers. Basically covers almost everything, every 3,5 compound except the nitride. So all the metamorphic, the HEMT, indium phosphide HEMT, HBT, they are all being currently used in much bigger quantity that we could have imagined before. Okay, and also our customer keep asking us to push to higher and higher performance. Although these are all small increment improvement, we are not making quantum leaps, but that still keep this job interesting. So just two technical slides. One thing about the manufacturing mass production of MBE is uniformity. You are spraying atomic beam to a platen about this big. You want that layer you grow to be uniform. That's not easy. So we are demonstrating we have to modify the cell design, even the MBE chamber design, to make it uniform. This is a platen of 4 6-inch wafers. You can see that on the upper right, 4 6-inch substrate. And we were growing a VXL, 940 VXL structure. And you just look at the reflectance, and then from 5 different spots along that radius, you can see that the uniformity is very good. This is another demonstration of the same size platen, and it's a little busy. You can see that we can load a 3-inch substrate, okay, different center, a middle ring, and outside ring, or we can load 4 6-inch substrate. And if you just look at the Fabry-Perot dip uniformity from center to the edge, only after 6-inch outside 6-inch diameter, you start to see some drop, and that drop is still less than 0.5%. So that is the current status of mass production MBE tool is able to achieve. So I don't have too much summary here, just showing a picture. This is in 2015. I came here to attend the PA Symposium with Qualcomm, I think hosted by Qualcomm Group. And I was able to contact Professor Wieder and had a coffee at right outside the building. So it's to me it's a privilege to have the opportunity to work with Professor Wieder, and he'll be dearly missed.
Thank you, Patrick, for a very nice summary. Now it's Hong Ho from Intel.
Thank you, Charles. Yeah, so I was here from 1990 to 1993. I was the third graduate student in Charles' group. Patrick was the first one. He spent a lot of time in getting the gas source MBE set up. So when I joined, the machine was up and running. So I pretty much it can start the research work right away, is a beneficiary of the capability. But in early days, the MBE is not as reliable or mass production tool as Patrick showed in the IntelliEpi. So you may remember MBE as a molecular beam epitaxy, but it's also a megabuck evaporator of many boring evenings. So when the machine is up and running, we try to run as many experiments as possible so that we get many students using the same platform. We will try to get many things done. So Harry is on my thesis committee as one of the 5 members with Charles and late Professor Bill Chang and Professor Lu Xiam. He was here before, previously, and then Professor Bob Dyens. So I still remember for my final thesis, of course, Charles spent a lot of time review and edit and giving guidance. And I sent a draft to Harry a couple of weeks beforehand. He was the only other committee members read it. It made a lot of comments, and I got it incorporated in my final draft. And over the years, I have really benefited tremendously from his advice and guidance. And when I have a question, I go to Harry, but he always gives me a lot more than I asked. So it's very often, when asked one question, he stimulated me, say, have you thought about this? Have you thought about that? So that's really great. Even after I graduated, every time I came back, and when I see Harry, I always catch up with him. It's amazing. He always seemed to know where about me. I moved around quite a bit, but the last year in June, so I was still looking for Harry, but I was told he couldn't come. So I'm glad to be back. For different occasions to celebrate Harry's legacy. And I wanted to use this opportunity to talk about what I'm working on right now, the silicon photonics. I worked at Intel right now for almost a year, but the silicon photonics is a new thing, relatively new thing, and people have many definitions about integrated photonics. In silicon photonics, we specifically talk about the light is being transmitted and manipulated in silicon waveguide instead of, say, indium phosphide, which is often referred as a photonic integrated circuit, or in fiber optics. So this is somewhat related to Harry's legacy because in silicon, we use silicon mostly to make electronic devices. In the material, we manipulate electron to make it faster in transistor. But the silicon can do a lot of magics, but it cannot emit light. So what we do is combine the indium phosphide and then indium gallium arsenide material, which is one of the, as Karen discussed, it's Harry's favorite material. It's very well researched by him and many people over the years. So we get wafer bound indium gallium arsenide and indium phosphide material on silicon, and we leverage the CMOS technology to process a whole wafer of silicon. The wafer size is 300 millimeter. So we get all the passive optical components processed on silicon. Then we can get the indium phosphide, indium gallium arsenide quantum well material wafer bonded on the silicon material to build the optoelectronic active components. And when we finish the processing, we got the lasers bonded and integrated on silicon wafer. We can utilize the same technology, which is very commonly used in silicon industry, on wafer testing. So we can do optical property testing, electrical property, and high speed. We even go as far as on wafer burn-in. So when we all said and done, the device's known good die are formed on 300 millimeter silicon. So this is the silicon photonics process. Because we utilize the photolithography process to define the cavity length, and we utilize the indium gallium arsenide material as a gain region, so we can form the laser wavelength very precisely. For example, here it shows the 4 different wavelengths with the channel spacing about 20 nanometer from each other, and that's being used today in mass production for so-called CWDM, coarse wavelength division multiplexing in optical transceivers. The active devices, we have the laser on silicon, and we have silicon material as waveguide. We use electro-optic effect. That's really, in a way, our thesis work here, making modulators. I have been fortunate, even after graduated, for 26 years, I have always been working around the compound semiconductor material in lasers and modulators, photodetector transceivers, and electronic devices. So really the work done here to set a good foundation for my career so far. So this is one of the ways to make high-speed modulators, and basically it's a Mach-Zehnder modulator. You get light beam split in 2 arms. You use electro-optic effect to accelerate the light or slow down the light. And when they meet again, they interfere. And we can get a very high-speed modulator. So now we have light source. We can use the modulator, and we can get the light encoded with very high speed. Silicon here, we are used to manipulate photon, not electron, because the silicon had a band gap. It provides a transparency to the light at 1.3 or 1.5 micron wavelength. We got various type of passive optical devices researched and developed over the years. So they combine with the lasers, the modulators, the photodetectors, and MUX, DMUX, we formed the photonic integrated circuit. So what is it used for? Today, we use the silicon photonics to make high-speed optical transceivers. These high-speed optical transceivers are used to connect switches in a data center. If you use any type of social media, I'm sure you use Google, you're likely to use the transceivers that designed and manufactured in my group, because we make about a couple million this type of transceivers a year and supply to the hyperscale cloud service providers like Google, Facebook, Amazon, and Microsoft. The silicon photonics provides scalability and reliability, and it's really totally changed the dynamics, because the boutique industry of compound semiconductor, even in the industry, it is considered high volume if you make 50,000 devices. But for now, to start, we're making 2 million devices a year, and we can definitely scale up to provide enough transceivers to provide high-speed connectivity in the data center. The application and the capability of silicon photonics does not stop in data center, and we're using it to develop LiDAR sensors and fiber optic gyro sensors. This is for autonomous driving, and we can get, say, 60 or 128 lasers integrated in a small chip at 1/2 inch by 1 inch with 64 lasers. And in between, we have 4-stage on-chip semiconductor optical amplifiers to get the power boosted. And as you can imagine, so we can move into the smaller scale to provide intra-platform level and to connect between chips. So right now, the CPUs are connected through electric bus, and but in the future, as Intel CEO, new CEO presented in the Investors Day, we need to redefine Intel Inside. It's no longer just this a CPU inside a PC or a server, but it's more an XPU. XPU can be CPU, can be GPU, the graphical processor unit, can be FPGA, programmable field array, gate array, or SoC system on a chip. So the number of transistors are getting more and more. Right now on a big chip, they have as many as 20 billion transistors built on one chip. You can just imagine the amount of data need to be getting in and out. Up to some point, the electric bus will run out of steam, will need optical interconnect. So here, the silicon photonics in the front and center of this future definition of Intel Inside, which is the XPU platform inside of everything. It can be inside of a data center, inside a client computer, renewable energy construction, autonomous driving, household and industry, and security. So it would not be surprised that in the future, in your household, you have Harry's favorite material, indium gallium arsenide, as an optical bus to connect XPUs, to connect SPU with the memories to provide high compute power, to provide high bandwidth for connectivity. So thank you. So his legacy will continue to live, and this silicon photonics can be as pervasive as any electronics consumer devices at home.
Thank you, Hong, for giving us a glimpse of the new technologies. Yeah, so it's great that we have heard so many different talks on different technologies by different students, or former students and colleagues. I also hope there will be some collaborations that can result. Okay, so now it's my so my talk before the open mic session. Okay, so. I think I met Harry the first time in 1987 when I came to UCSD for interview. I might have met him earlier in the conference, but I don't remember. But so at that time, I was at AT&T Bell Laboratories and working, using MBE to grow gallium arsenide, aluminum gallium arsenide, two-dimensional electron gas structures for high-speed integrated circuits. And at UCSD, Walter Kuhl was just recruited a year earlier from Cornell to establish a high-speed circuits and systems group. And he was given several faculty openings. And Harry was able to convince him to give one of the openings to me. So he's very instrumental in getting me to UCSD. And as yes, at that time, Harry already many mentioned he had a solid source MBE system, like most other people. So to be different, I decided to set up a gas source MBE system, like Patrick said, so that I can grow this phosphide and related materials in addition to arsenides. And I was, and Harry helped me really a lot because he, through his connection and recommendation to Max Yoder at the Office of Naval Research, I was able to submit a proposal to work on gaseous MBE of indium phosphide, and got the proposal approved before I came to UCSD in September 1988. And so he was really a great mentor in that way, connecting me, helping a young person to start up his lab. And it was a very needed grant because my startup package was I was able to purchase only an empty growth chamber with my startup package. So, but with this grant, I was able to purchase pumps, diffusion cells, and other components to, but more importantly, I was able to have students, Patrick, Bing Liang, and Hong Ho, to join my group to make that MBE system into an operational one. So, yeah, so for this, I really thank Harry. And Harry also helped me in another way. He helped me to catch a rat. Because in 1989, Rockwell Science Center donated a used MBE machine to me. They just purchased a new one and they put the old one in the parking lot, for 6 months. It was wrapped in the plastic but for 6 months under California sun, and the plastic became brittle. Okay. Anyway, when we moved the machine in front of the engineering building, Unit 1, and when we opened up the plastics, 3 rats came out. Okay, so apparently, the baking jacket, the bake-out jacket for the machine was a very cozy place for rats. Yeah. So we moved the machine into my lab, and well, it was very smelly. Okay, so we had baking powder and so on. Okay, in there, and out came another 3 rats from the nooks and crannies of electronics racks. Okay, and I remember vividly the Harry and 2 environmental EHS, environmental health safety staff. Okay, 3 of them use a bucket. Each one has a bucket trying to chase a rat which was running along the wall. Okay, they caught it. But to this day, I don't know what EHS people did with the rat. Yeah. Now there is 2 other rats were caught or killed, but that's another memorable saga. I did not have photographs for those, but I'm sure Patrick Chen can. He was a witness. Yeah. So anyway, that was a very memorable moment, of Harry chasing the rat. Yeah. So So then also in '89, because I was very grateful that Harry was such a good mentor to me. So I organized, as I mentioned, this a surprise symposium for him for his 30th birthday. And so now I'll just go through some photographs, okay, that I have. So this one is in 1992, I think around June, and I was holding Mikoi Chin's baby. So Mikoi was also a student of both Bill Chang and Harry Wieder. So he saw Harry Wieder there. And this was in '94. I think that was when Patrick attended the commencement. So we have Harry and Dora and there. And then I think this picture was shown earlier. It was in 1997. And I think that was to celebrate Bill Chang's early retirement. So we saw, or the next picture, we saw Margaret Chang at the others at the end. And then this was a picture of, a group picture. Harry was also very active in Departmental Affairs. So this was taken in '97 at a department lunch meeting. And I just noticed, I'm the one in the back taking pictures. And here I got a picture of Harry fooling Alex. Yeah. This was a picture I think shown earlier too. It was Don Shaw on the left, who retired from Texas Instruments and came to the department for maybe about 6 months. Yeah, so we had a welcome lunch for him, and we saw Bill Chang here and Ed Yu, Ss Lau, myself. So actually, I was in the picture. Peter Asbeck, Paul Yu, Harry, and Huilin Luo. Yeah. And this is after lunch, so we had a picture in front of EBU1. And at that time, there was no bioengineering building yet. Yeah, so just another picture. Yeah. So we also, so this is in 1999. So again, it's an EDM luncheon, and then we had a walk at the La Jolla Shores. Yeah. Oh, and here this is SS Lau, and this is a Dean D. Rudy, Bill Chang, Michelle, Harry, you here, Karen, Karen. This was in year 2000, and I think this is when after Ed Yu got married. So Ed Yu here and his wife. Here is Yu Lo. So it's another picture after the dinner. Yeah. And so some other picture of this occasion was shown. So it was my 60th birthday. So we had a party, and here Harry is talking to Charles Chang. Yeah. And Harry is talking to Margaret Chang. So in 2011, so this was on the occasion of Bill Chang's 80th birthday. And so Harry was giving a speech there. And we had so Hong Ho, Harry, Bill Chang, myself. So Hong Ho and Cynthia, Cindy, and Peter Asbeck, myself. And we have Peter Chu. So that's Harry's first student. So Peter is sitting in the back. So this is my last picture. It's a Harry. So he has his coffee friends, Manny Rothenberg and Dave Sauter. So Dave Sauter was here earlier. So here, it's 2015. So that's when Harry was 95 or something. And so he still drove and had coffee with his friends. Yeah. So in short, Harry is missed. Yeah, I think we all miss him. Okay, so this ends kind of the formal program, and now we have open mic, and Rachel is going to read what Juan Fernandez wrote. And Juan is in Spain. Yeah. Thank you.
Okay, just pretend I'm Juan. Is he? Hi. Good afternoon, everyone. I would like to thank the organizers of Harry's Memorial Symposium for reaching out and allowing me to participate in this session, albeit remotely. Special thanks to Karen, Charles, and Rachel for keeping me timely informed and engaging me in Harry's remembrance. And of course, thanks to UCSD for embracing all of us after this time in a venue that to me still feels like home away from home. I first met Harry back in 1989 when I was seeking to pursue at that time a blurry interest in the area of 3-5 semiconductor heterostructures. I remember my first conversation with him, in which he gave me a tour through the chart of the energy band gap against lattice constant of 3-5 and 2-6 materials, and showered me down on how valence and conduction bands, Fermi levels, defect states, dislocations, interface and surface passivation, accumulation and inversion layers, quantum states, waveguides, superlattices, and more came together to allow the realization of new and advanced electronic and optoelectronic devices, and that these could be realized through molecular beam epitaxy methods. He explained all this to me with great scientific excitement and in a humble way, making me feel that he himself was in the process of exploring the same world I was about to enter. I left his office thinking to myself that this was exactly what I wanted to pursue, as it brought together solid state and device physics applicable to novel devices and circuits. And I knew for certain that I wanted to pursue this under the mentoring of Harry. The next day, he gave me an infinite source of references to read, threw me into the dungeons of the MBE lab, and, in essence, told me to come back after I would be able to present to him an original idea to pursue. Well, I thought then whether I had made the right choice. But really, this first interaction and the many that followed have been my most valuable learning from Harry that I continue to apply to this day. Be confident in your capabilities. Be curious with excitement. Do learn and train yourself in the subject matter you decide to pursue, and be humble in your knowledge so that others can learn from and with you. It is my motto that I strive to apply in my professional and personal life. It has accompanied me from my tenure at the Imperial College in London as postdoctoral research in silicon and silicon germanium heterostructures, through my time as technology deployment manager for Lucent Technologies, AT&T Bell Labs in Madrid, and later BP Solar deploying advanced photovoltaic cell and module manufacturing techniques, and finally, as head of asset management of utility-scale photovoltaic installations at both Sun Edison and now Sonadix. I have always felt Harry was accompanying me in this journey, and in spite of the distance. I also had the luxury of meeting Dora on a number of occasions, having a glimpse at his personal life. He was proud about his family and achievements of all in his closest circle, and being able to peek into his more private world made him a larger man in my eyes. Many years later, I was comforted by Harry supporting me during a most difficult and painful morning with kind and wise words that clearly came from a man who had seen and experienced great suffering firsthand and who had the solidity to come out of it stronger. Harry has been, still is, and I know for certain that he will continue to be a lighthouse for me and my family. My children today ask me, who is this man I talk about so often? My father, to this day, at 85 years of age, proudly remembers the only time he met Harry and the lasting impression he left with him. A source of guidance, direction, refuge, and inspiration, he will continue to shape us going forward as scientists, professionals, individuals, and more importantly, human beings. He is one of the last of a generation who lived firsthand the consequences of failed societies and who found strength in this very failure to work hard to defend values larger than all of us, promoting with rigor and discipline the development of open societies, enhancing creativity and critical thinking. I know he will live in me and my family for years to come. Thank you. Juan M. Fernandez.
Yeah, thank you, Rachel. Harry has mentioned to me several times, in my career that the purpose of being a professor is education, not just doing research alone. And so I'm very glad to see that, his students, my students, and other students, have all turned out very well. So now it's an open mic. So I just wonder if there are any people who, okay, we have Peter. Yeah, Peter Chu.
Hi, I'm Peter Chu. I was Harry's third student to graduate. There was initially 4 of us, Jim Roach, then Cynthia Hansen, and then me and Janice Veteran was in there. I started with UCSD back in 1982. When I started, I was a joint student with both Bill Chang and Harry. Initially, Harry didn't have much of a lab. So what they did is they sent me down to Naval Ocean Systems Center. And I actually worked under Art Clausen, but I was a graduate student here. And I worked on chemical vapor deposition. I built up an indium phosphide as well as germanium hydride CVD system. After about 2 years, they decided that I was too remote and they wanted to bring me back. And at that time, I was the student who had a lot of epitaxy experience. And so Harry was in the process of getting a new MBE machine. And so Harry and I basically planned out the lab. And I think a lot of you students who were in the hot seat probably saw a photo behind you on the wall of the MBE machine hanging from a crane as it was being delivered into the AP&M building. So at that time we were in the AP&M building, and they had to bring it by crane into the side. And then we moved it down the hallway and put it in there. So that was quite a long time getting it into there. Eventually we moved to EBU1 and we had to move it over here. I might have been Harry's longest student because at that time the university didn't really push you out very fast, but later on they started pushing students out. I think by the time I graduated, I had published 17 papers with Harry. And so it was quite a long time. Since after that, I actually went to Hughes gallium arsenide operations, which was a gallium arsenide foundry in Torrance. About 8 years there before it was purchased by Raytheon, and they closed us down. So then I bridged back to Hughes Space and Comm in El Segundo. Then that in 2000 was purchased and became Boeing. So currently I am manager of advanced technologies for the Space Electronics Group under Space and Launch, which is a division under the defense side of Boeing. So fast forward, about 2015, my father, who was a professor of physical chemistry at Stony Brook University in New York, he decided to retire. Retire at 83, 84. I guess professors like to, they never retire, basically. So him and my mother packed up and moved out to go to a retirement home called V in La Jolla. And so not only did they end up in the same facility as Harry, not only did they end up in the same building as Harry, they ended up on the same floor as Harry. 3 doors down from Harry's apartment. So whenever I went to visit my parents, I had to walk past Harry's apartment. But I'm grateful for that because it allowed me to reconnect with him. And one of the key things is that I was able to bring my wife and my 2 daughters to visit Harry. Now, they had met him when they were very small, and then now they're in their 20s, but we were able to meet with him, and over the last 2 years, during that time from 2015, they were able to, every time they visited the grandparents, they were also able to visit with Harry. So I am grateful that we were able to reconnect and have dinners together and so forth. So one final thing is, I know you guys have been putting up that band gap and lattice chart. I have the original. Harry had copies, well, not copies, but when he originally got them, there were actually photos, the color photos of them. And I have one of them, so I'll try to scan it and send them out to everybody. But it's the color version, so. All right, thanks.
Yeah, thank you, Peter. Yeah, here before we continue, I want to actually acknowledge two people. One is Stephanie Battaglia. So she is really organized the whole events for us. And the other one, is Professor Trong Nguyen, sitting in the back. He was the previous chair, and he funded today's event. Yeah, so thank you very much, Trong. So now there are other people who want to, yes, Shadi, yeah.
Good afternoon. My name is Shadi Daya, and I've had the pleasure of meeting Harry after I joined UCSD as a faculty member in 2012. So our interactions were limited, but they were always meaningful, and there was always something to be learned from Harry. You may say that most of you have known Harry in a different era, but Harry is Harry. He was consistent for who he was and what he stood for throughout, and mentoring and education were center and front in all his interactions. And that was not only at UCSD, it's actually in the broader electronic materials community. I think Alex mentioned about one type of laser, the DFB laser, that was invented at Bell Labs. And there's another type of laser called the quantum cascade laser that was also invented at Bell Labs by a scientist called Federico Cappasso, who's now at Harvard, and who happened to host me for a talk in 2015. So similar to how Ed's advisor told him as he was coming to UCSD, get to know Harry. And when I, as a graduate student from Ed's lab, Ed told me, get to know Harry Wieder when you come to UCSD, I was telling Federico that about my interactions with Harry, and he told me the following: please deliver my fondly regards to Harry. He is someone who encouraged me as a student when I was working on multiple quantum wells. He's excellent, and he's also a caring individual. So this is not his student, he's someone who met at a scientific conference, and he felt that he should encourage him to do well in his career. And then later on, he moved to Bell Labs and did these exciting things at Bell Labs and now at Harvard. So Harry was incredibly insightful, exceptionally eloquent, and genuinely kind. And he had an undiminished courage to always state what's on his mind, which was usually right. And because he understood that it will have good consequences over the long run, and we've seen a quote earlier in David's talk, even if that truth is bitter at times. So this is something that many of us aspire to. And it's because of his courage that he had always beaten the odds throughout his life. Even in his passing, he has beaten the odds. We often say the good ones leave us early, but for Harry's case, we can say it was never enough. And maybe there's a lesson for us to learn here, that our common wisdom diminishes at the feet of purity because Harry was pure. He had a profound care for the electronic materials and devices program in our department, and he knew that when Karen Kavanagh left by the year of 2000 and then EDU in 2009, that we've lost two essential pillars of research in materials and devices, microscopy and spectroscopy. And then Charles Tu and Paul Yu's effort in the growth of compound semiconductors were also winding down. So he felt that the program is being crippled. And he also sensed early on the political wave that's sweeping the country, stating many times history is repeating itself, and some of us did not learn. Despite this, Harry always projected a message of hope. And the truth is that whenever I met him, I saw a sigh of relief in his face that we're still managing to keep the electronic materials program in our department going, somewhat with the help of the national user facilities, such as the one at Los Alamos and Sandia National Labs, and with our institutional support that we hope to grow moving forward. So that's why I feel that the Harry Wieder Electronic Materials Excellence Award is timely, and in fact fulfills Harry's wish for continuing this line of work at UCSD. So I cannot say enough thank you to the Harry Wider's family for establishing, committing to, and financing this award, and for the past ECE chair, Trong Nguyen, who has also dedicated $50,000 in support of the award and this symposium. Last June at the Electronic Materials Conference, Rachel Goldman, Edu, and I thought about bringing everyone who was touched by Harry's kindness and influenced by his intellect to celebrate his memory and acknowledge his influence on our career paths. I know that there were many who wished to be here and have shared their touching memories in writing or in video, and some I know are watching us live right now. And I can say that Harry was proud in his life of all of you, and I'm sure he's smiling now as he's looking at our gathering. So today's event happened with the generous support of the ECE department. So thank you again to Trong Nguyen and to Bill Lin, who have supported this symposium and financed it, and to Stephanie Battaglia, who made it happen, and to Charles Tu, Rachel Goldman, and Peter Asbeck for their help in planning for this symposium. And thank you for everybody who traveled from throughout the world, another state, or the local colleagues. Thank you.
Yeah, thank you, Shadi. So, anyone else? Okay, so now we have we formally close the speaking part of the symposium. So now it's time to catch up again outside. Yeah. So we have a reception going until 7:30. So we are just right. Good. Thank you.